Welcome to the second day of BTC++ Consensus Edition. Our first guest is Russell O'Connor. He will bring us in the world of formal functional correctness. So give him a warm welcome. Thank you.
Hello, everyone. I wanted to begin with looking for some thoughts that people have on the aspect of the programming endeavor. I found two quotes that I liked. Software is written by humans. Well, maybe a little out of date. Software is written by humans and therefore has bugs, right? So writing software is a human endeavor. And this amusing one by Ellen, the job of putting bugs in is called programming. So it's sort of the opposite of debugging is programming. But more seriously, there's a question about, is it even possible to write correct software, right? Is it something that humans can do? And before tackling this question, we'll move on to a slightly easier question, which is it possible to write correct mathematics? Because mathematics is sort of an endeavor that feels like it's rigorous, and it has a certain quality of correctness to it, or perfection. Maybe that's a bit of a strong word to it. And so I want to talk about this to begin with, the ability to do correct mathematics. And the best way to do that for me is to tell you the story about my journey to being on this stage today. And it starts back in the 1990s. And if you remember the 90s, it was basically the golden hour of Western civilization, right? The Berlin Wall had fallen. The Montreal Protocol had successfully banned CFCs and started reversing the ozone layer depletion. And we can actually pinpoint the pinnacle of Western civilization in a particular date, September 1993, right? Historians now call the era following that day, that month, the eternal September, and it's all downhill from there. It's not all downhill, because there have been good things that have happened since then, and we will see some good things that have happened since then. But I entered university at the University of Waterloo in 1995. I entered their mathematics and computer science program. So I studied mathematics there. And at the beginning, we had our first lessons in calculus and basic number theory, which would go on to be, in fact, one of the first things we did was the RSA cryptographic algorithm in like one of the third or fourth weeks of my first year university, which was very influential, I guess, on me. But the way that mathematics was taught was that the professor would do some proofs during class up on the chalkboard, and we would have lecture notes as well, which would have proofs in there, right? But no one explicitly taught us, what a proof was, right? We sort of had to learn it through osmosis, sort of infer, right? These are the things that make logical arguments. Other things are not logical arguments and are not valid proofs. We sort of proceed in this way. It wasn't exactly mimicry, because there was a certain understanding that you would get from the professor, although the difference between mimicry and understanding in today's age is maybe a little bit tenuous. But anyhow, we had homework assignments. I would do homework assignments. I would get many questions right. I would get many questions wrong as well, and not get perfect. Every once in a while, in fact, I would submit incorrect proofs that gave me full marks on my homework assignment. And then I would come back, and I would be reviewing with my friends, and I'm like, oh, my argument is totally wrong. I don't deserve those points over there. But it was sort of an ad hoc process until one day I took a course in formal logic. And it turns out there's a methodology behind what is, in fact, a correct proof in mathematics. And this was a bit of a surprise to me. I was equally surprised to learn that there's this Riesz algorithm for computing antiderivatives. Right? Why was I struggling through all those homework assignments to try various random things to compute antiderivatives in my calculus courses when there was an algorithm. And the same thing is true for what constitutes a mathematical proof. And so the question is, like, why was I making a mistake on my homework assignment? Like a methodology that will like guarantee whether I get it correct or not. But unfortunately, moving from the theory of proof theory to practice of proof theory is sort of easier said than done, right? And then part of the issue is that when you take a course in formal logic, what you study is a structure for formal proofs that are suitable for understanding the limitations and the nature of mathematical proofs, and not the practice of doing mathematical proofs, right? So you'd do things like the incompleteness theorem and other things like that. And it's very analogous to, if you've done computer science, right, the theory of Turing machines, right? The theory of Turing machines is there to be studied to understand the limits of computation, various diagonalization arguments, right? The undecidability of the halting problem, right? But Turing machines themselves are not designed for the practice of programming, and nobody goes around programming Turing machines except for very contrived cases. So after I graduated from the University of Waterloo, I went on to Berkeley, where I met a student there who introduced me to what is now known as the rock prover. And this is a system for actually trying to do the practice of formalized mathematics. It's a piece of software. It's evolved a lot over the 26 years that I've been working with it. And it's based on this notion of dependent type theory. So it actually is sort of a merger, unification, somewhere in between sort of functional programming and mathematical deductions. It sort of unifies those two things into one language. And we can actually do mathematical proofs using various proof of systems. There are, of course, other things, like Lean is very popular today, Agda, and there are other ones like Hall-Light and Hall that are not based on dependent type theory, right? But the theory, the practice of doing formalized mathematics has really been been evolving quite a bit over time. I spent some time at INRIA doing the proof of the odd order theorem, which is a famous mathematical theorem that like took 2 volumes of books to prove, and I did a small part of that proof in a collective effort, right? So that was sort of one of the biggest, at the time, milestones in the development of formalized mathematics, right? So I was able to take the theory of proofs into sort of reality, and what we want to do is bring this to bear on our problem at hand today, which is the problem of modular inverses, which is not the most difficult mathematical concept in the world. So let's do a brief history of the safe GCD algorithm, which is the new algorithm that, well, not new now, right? But at the time, new algorithm for computing modular inverses. They're a key component of cryptographic. It's a key cryptographic subroutine. And the problem is you're given some value x, and you want to find some value y, such that x times y is equal to 1 modulo p for some prime number p. And the basic algorithm for doing this can be traced down to one of the first proof correct algorithms, the Euclidean algorithm in 300 BC. Euclid has an algorithm for computing the greatest common divisor of 2 numbers. And here I'm showing you the Bezout identity for the GCD. And you can sort of see the relationship between common divisors and this equation here, right? Because if we want to find a common divisor between p and x, is that we say that if d is a divisor of p and d is a divisor of x, i.e. it's a common divisor, then it's going to be a divisor of this integer linear combination of x and p. And if we can find values y and k such that this equation is equal to 1, then we will know that the divisor also d the hypothetical divisor of x and p, the common divisor, also divides 1. And if something divides 1, then it has to be 1 or negative 1, right? And so this Bezout identity is sort of an equation that lets you prove common divisors, and when it's equal to 1, that means they have no common divisors at all. And this will, of course, be the case if p is prime, right? Because p doesn't have any divisors other than itself. And if x is less than p, then their only common divisor will be 1. Which is all to say that there does exist these Bezout coefficients y and k that will satisfy this equation. And then this is really just a rearrangement of our modular equation above. If we can figure out what our Bezout coefficient y is, we've solved our modular inverse. So fast forwarding about 2,000 years, Bernstein and Yang come up with this alternative variant of the GCD algorithm called safe GCD. Now, I have skipped over a lot of mathematics in those 2,000 years, right? They are not the first person to adjust the GCD algorithm or come up with a variant of it. But they had a particular goal, which is relevant for cryptography, of coming up with a constant time algorithm for doing it. Previously, we didn't really have a constant time algorithm for doing it, and so we couldn't use the Euclidean algorithm for computing modular inverses. We generally used an alternative called using Fermat's little theorem. However, the Euclidean algorithm is much, much faster to compute than using the Fermat's little theorem. The only advantage of Fermat's little theorem is that it could be done in constant time. So coming up with a constant time GCD algorithm was a big deal. Peter Dettman implemented the safety GCD algorithm by Bernstein, and it got merged into libsec-p 250K1, which is the cryptographic library underpinning Bitcoin. This was done in 2021 AD. So the question is, how do we know that this fancy new algorithm that Bernstein and Yang derived is actually correct? And so the safe GCD algorithm, I'm not going to describe it in detail, right? But you've got these sort of 3 invariants. And what happens during the algorithm is that we apply a bunch of various integer linear transformations to f and g to manipulate their values and iterate it several times. And we're trying to convert f and g from their initial values of p and x down so that f is equal to 1, or it could also be equal to -1. And we can see that from our top invariant here, we're computing this d and e as we go along. And if we could get f down to the value 1 or -1, then by our invariant, x times d would be equal to 1, and d would be our modular inverse. And if f was equal to -1, then negative d would be our modular inverse to solve the problem. So it's actually easy to show, even in first-year university mathematics, so that if this algorithm terminates, then it's going to correctly compute the modular inverse. But the big difficulty is in I haven't described exactly the algorithm, but that the values of f and g shrink in absolute value, and eventually, if they keep on shrinking, then f will become 1. So there's this complicated algorithm in Bernstein's paper that uses this thing called spectral radius of matrices that I don't even understand myself. In order to prove termination. But Peter Wille of Bitcoin fame, he came up with his own termination argument, basically putting a convex hull around all possible inputs. And because we're doing linear transformations, we can sort of do linear transformations of these convex hulls. We have a bit of choice in what matrices we use. And so we sort of take the convex hull union of all the possibilities. And we sort of iterate this process, and we can see that the convex hulls shrink and eventually get down to 1, and we can count the number of steps and determine the number of steps to get to termination, right? And so this computation that Peter Wille did was verified by a Python program that he wrote, right? And so, but is it really a proof in mathematics when you use a program to do the verification? This is a question that comes back to the famous four-color theorem. I mean, there's a certain logic to that argument. But when this PR was up for inclusion in libsec-p, I thought I would check Peter's program by re-implementing it myself. So maybe doing a second implementation would help satisfy us that this was correct. So I re-implemented in Haskell, which is my particularly favorite programming language, and that was successful. And it, of course, had the same result because Peter's Python program is not wrong. But then I was like, well, Haskell is very similar because it's a functional programming language to the rock prover's internal language. So I re-implemented it again in the rock prover, right? Just the program that does the analysis of the convex hull bounds and see how to figure out how long it would run, because the rock prover is not a compiled language; it's an interpreted language, and a pretty slow interpreted language at that, right? But it was able to run in like a couple days, depending on exactly what mode you do it on, right? Which was a long time, but you just need to verify that it works, and so that was fine. So all that was needed to do was then to like connect the fact that this convex hull program successfully terminates to the mathematical fact, because that's just a program that does a bunch of convex hull computations. Like, what does that have to do with the safe GCD algorithm, right? So we need to prove the correctness of this Python program re-implemented in the rock prover that says that the successful termination of the execution of this program means something about the safe GCD algorithm, right? So we have to prove that the convex hulls have something to do with the parameter space of the safe GCD algorithm that it iterates. So there was a bunch of work to do proof of a correctness of this inside the rock prover, and we completed that with Andrew Polstra in 2021. And so that successfully showed that the algorithm for doing the safety GCD algorithm was correct. And at that point in time, it was merged into libsec-p, and then eventually made its way into the Bitcoin release, right? And this demonstrates sort of a very powerful proof technique that is just not available when you're on a blackboard on campus, right? We have an intertwining between proofs and programs in dependent type theory because the language is unified, right? Proofs can reason about programs. We prove the correctness of a program. But then these proven correct programs can actually be executed inside the environment of the rock prover. And the conclusions of the execution of those proofs, those programs, in fact, yield mathematical proofs. So this is why I really love dependent type theory as a way of formalizing mathematics, because it gives you a tool that just doesn't exist on a chalkboard, right? You can't execute a program on a chalkboard, but you can execute a program in a proof assistant. So that's all well and good, but when the code that was merged into libsec-p looks in part like this, right? And how do we even know that this code here implements the safe GCD algorithm, right? We proved the algorithm is correct and terminates and computes modular inverses, but have we actually successfully implemented the GCD algorithm? And so that brings us to the question of implementation correctness. And this also has a history. It's not as long as the history of the Euclidean algorithm, but Tony Hoare introduced, and Floyd introduced this notion of a Hoare triple, which is fairly famous in computer science, which talks about the correctness of a piece of code. You have some sort of precondition written in logic, and you say, if the precondition is satisfied after we execute some particular block of code, then some postcondition will be satisfied. So many years passed. Wells introduced this notion of a separating conjunction, which we'll talk about in a moment, as a new logical symbol that appears in the preconditions and postconditions that's different from the mathematical logic symbols that we're used to. And then Yang, in his PhD thesis, proved the completeness of the separation logic in 2021 AD, right? This means that everything that you could want to state about the execution of a program can be proven using the axiom system of separation logic. So I just want to give a very, very brief illustration of separation logic. Right? This is a little fun piece of code that maybe not all of you have seen. It's a fun way of doing an in-place swap of the pointers to two values. You can think about that a little bit, on how that works, right? But I'm more interested in the logical structure here of our preconditions and postconditions, right? So here we have a precondition that says P is a pointer. It's pointing to some memory cell whose contents contain the value I, and Q is another pointer, and it's pointing to some memory contents that contain the value J. And the star is the separating conjunction that was invented by Reynolds, and it says not only are these two statements true, as part of the asserted true as part of the precondition, right? The heaps that those are referencing are disjoint, and so these two pointers P and Q don't alias. Because if P and Q are aliasing pointers, and you run through this algorithm, you find out quickly that it just returns 0 at the end rather than swapping the two values. So the fact that P and Q do not alias is important for the correctness of this program. And so you would go through the logical steps of reasoning in a separation logic, and you would conclude from this program, because you have the separating conjunction that proves that that asserts that these are not aliasing pointers, that in fact the postcondition is that P now points to J and Q now points to I. Now, with Hoare logic, you can add to your logical system that says, P and Q are not aliasing. The problem is that you sort of get this exponential blow up as your programs become more complicated, saying X and Y and Z and T and Q, they all don't alias with each other, or maybe they do in some circumstances, and it becomes completely untenable to do it. Whereas separation logic collapses the notion of not aliasing into a logical system symbol. And furthermore, it also states that there's a heap outside the precondition and the postcondition, and whatever is going on in the heap outside that is also not touched by this program, which is something you would actually have to state if trying to do Hoare triples. So this is a nice quote from the 2016 Goodall Prize citation. For the last 30 years, experts have regarded the pointer manipulation. So pointer aliasing is the crux of the problem. Hoare triples cannot handle pointer aliasing in a reasonable way. So they've regarded pointer manipulation as an unsolved challenge for program verification, and shared memory concurrency as an even greater challenge. Now, thanks to concurrent separation logic, both of these problems have been elegantly and efficiently solved, and they both have the same solution, which is a really fantastic result, which happened well after I graduated, so I did not learn about this in my computer science class. So progress continues. The verified software toolchain out of Princeton is an implementation of separation logic, and it's implemented in the ROC prover. The semantics for it does separation logic for the C programming language. The semantics for C comes from the certs compiler. And yeah, we were able to use the VST toolkit to verify the correctness of the C code implemented in libsecp. Now, there's all sorts of fun stuff. There's a paper that's linked to in the program about things, close calls and bugs that I found, close calls to finding bugs in this that turned out to be fine. But what I want to really emphasize is that, that this is something that we can do. This is something we can do today. And what I want to emphasize is that the ROC prover was a key instrument to doing this procedure because it allows us to combine both the safe GCD proof of termination that we had done earlier with the separation logic, which is used to verify the functional correctness of the C program, and bring them together in one system so that it has access to all components. Often, program verification just outsources its problems to a SAT solver, right? But a SAT solver won't be able to derive that convex hull argument that Peter Willa did, right? And so being able to specify that and being able to import it into the correctness of the C code was nice. There are some caveats we need to be aware of. VST doesn't support passing or returning, and unfortunately, assignment of data structures. Constant timeness was not actually covered by the proof. The proof is just about the functional correctness of computing a modular inverse. And there's no real support for reasoning about C++. Anyhow, to wrap things up, I just want to say that there's an alternative to programming beyond the ability there's an alternative to programming beyond our ability to reason about the code that we're trying to write. We have the tools already needed to eliminate defects from our software, and we just need to slow down to use them. Humanity has always sort of grasped for the most expensive solutions to their problems, from software to constructing homes to climate change, so long as the upfront cost is as little as possible. We collectively spend inordinate amounts of time on auditing software, paying ransomware, patching 0 days, and so forth, right? And this all happens because we're coding beyond our ability to reason about the code that we're doing. And so that's why the order of the ordinals of computation of the faithful form, they live their lives to slow down. And they develop software and mathematics, which are really two sides of the same coin, as we've seen here, in a manner that's both reliable and sustainable. But you don't need to join an order in order to reap the benefits of using formal systems. Just learning how to use separation logic can really improve your coding, because you learn how to structure your code, even if you don't formally verify it, as if you could formally verify it. And so just having gone through that practice is very valuable. And in conclusion, this is your opportunity to pick up the torch. Remix 7531 has already made some strides, right? He's continued this work on the verification of libsubkey. He's verified the modular scalar multiplication algorithm, and there's no reason that we couldn't verify basically the entire contents of the libsec P256K1, the heart of the Bitcoin algorithm. So now it's your turn. Thank you.
OK, so just a quick intro. Hi, I'm Tadge Dryja. You may have seen me before. I'm wearing the T-shirt from an ancient BTC++. Work on Bitcoin stuff, Lightning Network, discrete law contracts, U-XO. Now I'm working on this stuff. So come, I don't know, there might be some time for questions. I kind of have a lot of slides. If not, come ask me around. I'll be here today and tomorrow. So quick table of contents. I'm going to talk about recovery. So the sort of 4 topics: detection, recovery, and then lifeboat, life jacket, and distinguishing. Sort of how I chop this up. But first, a little introduction of what are we doing? What's this problem? OK, so people talk about quantum computers, and they're worried that a quantum computer will destroy Bitcoin or something. Yeah, maybe. But we don't really know what could break Sec P256K1. Maybe it's formally verified, but fundamentally, there's no proof that the discrete log problem is anything. NP, no, is P NP? We don't know any of this stuff. Is SHA? Do hash functions exist? Do one-way functions exist? We don't know, right? So this stuff could break. Hopefully it doesn't. But some of the times, it is a little scary, because there's all these AI things, and they're finding new things. Is what if you're just hey, AI, find the algorithm for finding the discrete log of Sec P256K1. Make no mistakes, and it just spits it out. And you're shoot. Or if there's a lot of the quantum research. So some of the quantum research is interesting, because they're oh, we actually don't need as many qubits. We thought we needed 1 million. Well, apparently you only need a couple thousand. What if they get it down to oh, wait, you don't need any? And this whole quantum computer thing was just a way to figure out the way to do it with a normal computer. It's possible, right? So I sort of like thinking of it as post-elliptic curve. You don't know if it's quantum. It could just be anything that breaks elliptic curves. And I mentioned SHA-256. If SHA-256 is broken, I don't see any way that Bitcoin can be recovered. You're just totally screwed. Because also, if one-way functions don't exist, I don't know. Can you make a cryptocurrency? Whatever. But the elliptic curve being broken is a bit more of a threat. But fortunately, it is more tractable. So what if it breaks? That would be bad. We can use other stuff. People are working on things like shrinks, and so we just fork in shrinks and we're okay, right? Well, the problem is no one upgrades Bitcoin, right? So it's today, 2026, you can just go look at blocks, lots of new P2SH, not P2WSH, just P2SH non-SegWit outputs all over the place. And then SegWit has a very clear motivation to use it. Like, it's cheaper, the fees are lower, but people still use non-SegWit. And yeah, pay to Taproot, quite a bit less adoption. There's not much. So the problem to solve is, okay, we have these post-quantum output types. So I'm assuming we get something like shrinks or sphinx or shrimps or whatever. I'm assuming some kind of post-quantum signature scheme can get soft forked in. That feels not super controversial, right? It's like, hey, here's this new thing. If you don't want to use it, don't use it. It's this nice new opcode, new signature scheme in Bitcoin. I would use it. I would try it. Cool. Maybe most people don't. I think most people probably wouldn't. If you added this to Bitcoin, maybe some people who are like, oh, I just want to be secure, like, will move their coins. But for most usage, probably people would ignore it. It's fine. So let's say this happens, you have it, and then at some point in the future, elliptic curves break. And so even with years of warning, there's just millions of these elliptic curve protected UTXOs remain. What do you do? Okay, so I'll talk about what to do. But first, I want to do a little aside that, like, people have complained that, like, core, whatever that means, like, don't take quantum seriously. And I understand that, right? And people have even said to me, so I started working on this, I talked about this last year as well, but I got a grant from Maelstrom this month, so shout out to them. And I'm working on this stuff a bit now. I'm still working on UTXO and stuff, but this is an interesting thing for me. And even for me, people have been like, why are you working on that? Like, come on, And then there's this sort of idea that it's like not an interesting or not a valid field. So I think the criticisms are somewhat valid, right? Like, Bitcoin developers are sleepwalking towards collapse, whatever. It's like, there's FUD, and there's a lot of people complaining, oh, like, this is... But at the same time, there is a certain validity to, like, yeah, there is a resistance to working on this. There's a resistance to this kind of stuff from a lot of the experienced developers in Bitcoin. And I have some ideas why that I'll get to throughout the talk. I understand it, but I also think, and I sort of want to push back and say, well, even if this doesn't happen, like, working on defending against attacks that never occur is very much the Bitcoin way, right? So if you look at, like, any Lightning Network implementation, half the code is dealing with justice transactions, and, like, they never happen, right? If you go into your Bitcoin core folder, you have a blocks folder, and there's all those, like, rev 000.dat. That's also, you can all those files, and there's about, 80, 90 gigs of them now. Those are also that you can reorg back to 2009. It never happens. You never use those files, but they're all there, and it's taking up 100 gigs, or not quite. So the idea of, like, we will defend against this thing that may not happen, it's like, yeah, that's what we do in Bitcoin, right? Like, we're paranoid. So I think it's good to work. Okay, so options for dealing with these old coins. One is do nothing. And that would imply the coins get stolen, right, taken. And so I've definitely heard people say, hey, if you build a quantum computer and you can find these keys, they're yours. That's the agreement we bought into in Bitcoin. So, I don't think there's an explicit agreement, but yeah, okay, some people say, yeah, do this. Some people say, destroy all the vulnerable coins. That seems kind of a jerk move, if you can do better than that. What I'm proposing, and it's not a new idea, is some kind of post-quantum spending conditions for elliptic curve UTXOs. And that seems like a good compromise, right? Everyone will be okay. So the hard parts. Vulnerable coins and everyone. What are vulnerable coins? And yeah, everyone's not going to be okay, but hopefully most. So yeah, just defining these, and it's hard, and with the new conditions, you don't get everyone. Okay, so first though, detection. And, like, I think this is one of the tricky parts, is how do you decide when to enforce this? You need consensus, right? You can't just say, like, oh, tomorrow, like, we need to start enforcing post-quantum or whatever. Hopefully this never happens. So this is a weird one where it is kind of a downgrade, right? Like, all the different things in Bitcoin where we had P2SH, we had op-checks lock time, we had SegWit, we had Taproot. Those are good things. Like, it's great that we have those. We still use P2SH, well, kind of. But this is one where it's like we're really kind of making it worse, right? We're removing this whole cool elliptic curve thing, which lets you do frost and roast and signature aggregation, all these awesome things that people have researched for a decade or more. And that is one of the reasons a lot of people don't want to work on post-quantum, is because it's like, this trashes all of my work for the last 10 years. So I'm going to pretend this is not going to happen, because that would be really bad. But anyway, so you can make consensus like an activation of this enforcement based on consensus. I think this is a good way to do it. I think a really easy way to do it is you detect based on these two opcodes. You just say op SHA-256, op check sig. If you see those two opcodes and not, and they actually execute, not in like an op if 0 kind of thing or after an op return or anything, like they actually happen, okay, then you activate. You know that the elliptic curves are broken. At least sec p256k1 is broken, because basically you know that your node just verified a signature, and the pub key from that signature was just something you hashed. It was an output of SHA-256. So how can that be possible, right? The only way that's possible is if either SHA-256 is broken, and someone could pre-image that, or the signature system is broken, because the pub key, no one could have created that pub key by coming up with a random number, multiplying by G, and then signing, because they clearly must have come up with it by hashing something, not multiplying by G. So then you can activate. And I think that's a pretty straightforward way to code this in and say, look, if this happens, okay, enforce activation of this code. And it is also a weird new thing in Bitcoin where you're like activating based on something that happens in the blockchain. That's weird, right? That's never been, arguably, okay, mining decides how to activate, but this is like based on a transaction that you don't know when is going to happen. It's pretty weird, but should be doable. You could send, some people have talked about like bounties. You could send coins to pay to WSH with just those two opcodes. You could do that. I don't think it matters. It sort of feels like posting a reward, like I'll give 1 Bitcoin to whoever can fly to Mars and come back. It's like, okay, cool, Bitcoin's a lot of money, but the scale here, right? Like building a quantum computer or breaking SecP is like such a big deal. I feel like a bounty in Bitcoin is like, okay. And yeah, but then it gets complicated. Like what if someone has a way to break it, but they don't reveal, then you're in big trouble, and so on. So I think we hopefully have a situation where before too much gets messed up, we have a publicly verifiable proof that the elliptic curve is broken. And then we activate these things. Okay, so what do we activate? After detection, we have new spending conditions on old outputs. So this is a soft fork, which is good. If you haven't upgraded, you will see transactions that look like normal. You'll also see transactions with a bunch of extra data, like op returns and stuff, that still seems valid to you, but you ignore. OK, so there's 2 recovery options, extra conditions you need to spend your coins. I call them Lifeboat and Life Jacket. Lifeboat is for outputs with unknown pub keys. So if you've used pay to pub key hash, pay to witness pub key hash. Oh, and I don't talk about pay to taproot here. Pay to taproot is complicated. There are options. It's complicated, and there's lots of ways to do this. Not that there's no good way to do it. There's lots of good ways to do it, and it's like, how do you do it the good way? So it's kind of complicated, and also there's not very many taproot. There's a lot of taproot outputs, but not a lot of coins, and those are pretty active. So I don't worry about it too much, and there's ways to do it that are kind of complicated and don't really matter here. But you don't do these 2 things. So Lifeboat is like you have a pub key that's hidden, right? You have your address is on chain, and that's a hash of a pub key. And then Life Jacket is for all those outputs, and there's a lot of them. I think it's a minority, but it's still millions of Bitcoins where the pub key is known. So the address has been used more, not just reused as in received multiple times, but reused as in has received, spent, and then received again. Or received multiple times. Anyway, you know what I mean. You've received multiple times. There's UTXOs where you see it is a pub key hash, but I've already seen the pub key there. I know what leads to that pub key hash. Okay, so yeah, and kind of a silly name maybe, and the emoji is not a life jacket. It's a life preserver, whatever. But you don't want to be in. You want to be in the boat, not in the jacket. So don't reuse addresses. The boat is a lot nicer. The jacket, you get wet, and some people don't make it. Okay. But most people make it, so it's, yeah, okay. It's better to have a life jacket than just be in the water. Okay, so both of these use a commit reveal process, where so you can think of like prover verifier, but prover is basically your wallet, and verifier is your node, or everyone's Bitcoin node. So the idea is a prover makes a commitment, confirms it, so you got to get it confirmed in a block, and then reveals the transaction to the verifier, all the nodes, and then they make the commitment by buying some post-quantum coins. So that's one of the big problems with this is, well, how do you get data into the blockchain if all you have is these vulnerable coins? If we assume, and I think it's a pretty safe assumption, that we have some kind of Shrinks or Sphinx kind of hash-based signature in beforehand, the problem's a lot easier. It's just go buy some, right? So it's like, oh, I have like, a Bitcoin that's in this old output, and I need to move it because the quantum computer showed up or whatever, elliptic curve's broken. Okay, buy a few dollars somewhere of post-quantum coins and use those new coins to make your commitment. So that seems like a good way to sidestep all the complexity of like, how do we commit these things first? Okay, so the basic idea for Lifeboat is you've got your old output. You've also got a new output, or you ask your friend, who had, because you're only just paying a fee for a transaction, so it's very minimal. So you ask your friend, hey, can you commit this little ABC op return? It's like 96 bytes or whatever, right? The idea is H is a hash function, but it is not the hash function that was used for hashing the pub key hash initially. So like it's not hash 160 in Bitcoin is what you use for pub key hash. Which is like the ripe MD of the SHA-256 or something. But you don't use that. And actually, I think the good idea is to key all these hash functions with something that was not known initially, right? So like the activation block hash can be the key for all these things or something. So basically, it's the hash of a pub key, the TXID of the transaction you want to make, moving your old vulnerable coins to a new safe address. And then C is this sort of proof where it's the hash of the pub key concatenated with the TXID. And you stick those three things together, you confirm it in an op return. I'm not going to go into the details. It is secure even if someone front runs you and someone observes and says, oh, I'm an attacker, and I've got a quantum computer or a discrete log oracle. I see these three things, and then I flip a bit on B and confirm it before you. It's still fine. Or I can flip a bit. I can't put a new TXID with a valid use of that pub key because I don't know what these things mean. As an observer, even with a quantum computer, looking at A, B, and C, I shouldn't be able to understand anything about what you're doing because this pub key is unknown to me. So if I see this new hash of a pub key, I don't know what it is. The TXID shouldn't tell me anything, and then these two things stuck together. I can't do anything with it. I can flip bits. I can troll you, but that should be detectable. So the idea, all nodes store it in like a kind of UTXO set. This is one of the ugly parts. You basically store A:BC. So like A is the key and BC is the value in the database. When you see a transaction trying to spend from pub key A, right? So you say, okay, I see a transaction spending A. What is the hash of A that in the same hash that I'm using in my database? I learn A, right? I learn the inverse of A. I learn the preimage of A. And so I learned the validity of all these BC pairs, right? So back in here, once I learn pub key, I can see if BC match, right? Because I can take the pub key and then the TXID and see if, I take the pub key from A, I take the TXID from B, and I stick them together and see if B and C match. And so I can check validity of an entry. And so now I can say, okay, only the first valid BC pair is allowed. That protects front running after the confirmation. So you're protected against front running by the validity before the validation, before the confirmation of your commitment, as well as the confirmation of your spending transaction. Okay, so Lifeboat, I think this is pretty nice. I think in the whole talk, I'm not like advocating like we need to soft fork this or do this. I think this is a good way to solve this particular part of the problem. Because everyone knows their pub key, right? Like, of course, you know this. You have to know this in order to spend your coins, so you're not really imposing any additional requirements on the user. They have to upgrade their wallet, right? Their wallet software will need to be updated. Fine. There's a disadvantage. You got to get some post-quantum, some safe coins first, and you have to do 2 transactions instead of 1. I think given the scope of like, oh, we have to migrate all these old coins, like those are pretty minimal requirements. The key value set is probably the ugliest in implementation-wise, because now you've got this sort of extra UTXO set, and you got to keep track of all these things, and you can say, oh, well, you could spam it. It's like, it's no worse than spamming the UTXO set now, right? And you can kind of reuse the same code that we use in Bitcoin now, like you use LevelDB. But so I acknowledge this is kind of the ugliest part implementation-wise, but I'm like, well, it's not really worse than what we have today. You can already just make a bunch of fake UTXOs that just stay in that database forever, and people do, and it's annoying, but I don't think it's worse than what we have now. Okay, so that's Lifeboat. Then there's Lifejacket. Some degenerates have reused addresses, so Lifeboat doesn't work, right? So you can see here, if the pub key is known, this is trivially breakable. You don't even need a quantum computer. You just commit to a new BC pair that's just an arbitrary TXID, and you break this. So that's broken in this case. Can these degenerates, can these sinners still be saved despite their errant ways? So actually, in most cases, yes. Yeah, they're similar, and I'm going to describe similar to ZKP ideas, but you don't need to waste this elegant math on lowly address reusers. Okay, so the setup is similar to Lifeboat. So you still have this sort of like ABC, this triple, these 3 things. But instead of your pub key, you use what I'll call a pre-key. If you have better names, a lot of these names I'm just sort of trying to make up, including Lifeboat, Lifejacket. If you have better names, definitely let me know. What is a pre-key? And it's something, it's a little vague, something that comes before a key, like a pre-image for a key, but it doesn't have to be a pre-image. It can be anything that sort of leads to a private key. Or public key in some cases. It's complicated. But the simplest would be like if you have a SHA-256 pre-image of your private key. That is very easy to define, right? So in that case, let's say you do have that. Let's say your wallet works in a way that you hash something to get your private key. And you still have all that data, so you can provide the pre-image. So the idea is instead of your pub key, you say, okay, I'm using the pre-key here, TXID, pre-key TXID concatenated. And in this case, it's your pre-key is the SHA-256 pre-image of the discrete log of your pub key. Then, when you're spending, you first need to make an op return commitment before you can spend, just like in Lifeboat. The additional requirement is when you are spending, your spending transaction has to have this op return output as well. It just reveals the pre-key. Right, because one of the things, so the nice part about Lifeboat is the pub key is inherently revealed in the transaction spending it, right? Whereas this pre-key is not. The pre-key, if it's the SHA-256 pre-image, no one can see that, but you can just put it there, right? And did I say that? So you sort of line it up like SIG-hash single style. So if you have multiple different keys or multiple things going on in a transaction, in this case it's pretty simple. It's 1 input, 2 outputs. But you sort of think of it like a table, and you're like, okay, for this output, here's the op return. For this output, here's the op return. And at the end, you have a bunch of extra outputs where you want to actually send the money, and you reveal your pre-key there. And so the pre-key sort of takes the role of that pub key in the Lifeboat section, but would be unknown to a post-quantum attacker because they can't pre-image. And this is a little scarier because it like reveals your private key. Right? It's like, but in the assumption that like, well, that ship has sailed, we're in post-elliptic curve world, so it doesn't matter. Revealing your private key is the same as revealing your pub key. And you can say, well, wait, I don't know the SHA-256 pre-image of my private key. Nobody does, right? Like, what, you didn't use bitaddress.org brain wallet tab in 2012 to make your private keys? Like, it's still there. You can do it now, right? You can go make your private keys this way. And this is, or you could use, brainwallet.io, which does use, so like this is what I've been working on the last couple weeks, and it's like, oh, there's a lot of crazy ways people make wallets, and yeah, a lot of these are secure against quantum adversaries. You could use scrypt, but the last part of so scrypt on-chain verification, no, that's too slow. But the last part of the scrypt gets SHA-256'd. And also like Argon 2D and stuff, like all these crazy large hash functions that take forever to verify. They have this little step at the end. It necessarily condenses into a little hash function at the end that you can verify on chain. So it's great. So yeah, maybe these sites aren't like best practices, but they make your coins quantum secure. And so I want to rewind back to like, wait, why don't experienced Bitcoin developers want to work on this post-quantum stuff? And like, here's maybe a reason, right? Address reuse with a brain wallet. I can see this being somewhat discouraging for people who have been working on this for a decade and a half. Okay, BIP32 is the big one, right? So most private keys are not SHA-256 of some questionable entropy phrase. But most private keys are BIP32 derived, right? BIP32 is 2012, 13. I have this tab open somewhere. I've been looking at all the old key derivation paths and stuff. There's also like mini private keys. Anyway, but this is very popular. This is used in, I think, basically every wallet today. Yeah, not every wallet, but basically every wallet you look at, they're going to use they're going to use BIP32, not just in Bitcoin. Ethereum, everyone uses BIP32. It's great. Real sort of hand-wavy way that BIP32 works. I've dropped a couple of the requirements, but good enough for this case. You make up this hash called I. It's the hash of this like C, which is chain code, which is just some random bytes. Your private key, and I is the index, like 0, 1, 2, 3, what key you're making. So to descend, you basically take a hash, and then the kind of annoying part, I don't know why this is in there, it doesn't seem necessary, is your private key is this I, well, truncated, plus your parent private key. I don't know why that's in there. It would be nice if it wasn't. It'd make it a little simpler, but whatever. And that's hardened derivation. And then there's unhardened derivation, where very similar, but the idea is you use the serialization of the pub key in this hash, and then your public key is this I thing times G plus the parent pub key. And the private key is derivable as well because you just don't multiply by G and you add the private key of the parent. In this case, in unhardened, it makes sense why you have this plus K parent. In hardened, it doesn't really, but whatever. Keeps it symmetrical. Anyway, so you can do these things, right? And you can prove this. So in say, hardened derivation, you just say, look, I'm going to provide as sort of this pre-key in this op return when I'm spending C, K, and I. And the verifier checks that the hash of C, K, and I plus K itself that they got times G is the pub key. And that works in a very similar way to, hey, I know the preimage of my private key. I know it is sort of the preimage of your private key, right? It's a little more complicated, but it's a preimage of your private key plus the private key times G. So you gotta do it this way, but it works. What's actually kind of interesting, this is also has the scary property of, well, I'm giving not just giving my private key, I'm giving the derivation of my private key away in public in this op return when I'm sending it. I would say, well, yeah, the ship has sailed. We're already in an environment where you have a proof that, discrete log oracle exists, so who cares? But it is scary. Public derivation is actually okay. So if you have an unhardened key, you don't need to provide your private key. You can just say, well, I'll give C, K the public key and I, and then the derivation can be I times G plus K power. Because the idea is for an attacker to break this, they would say, given P, I'm a attacker, I have a discrete log oracle or a quantum computer, whatever. I see an address. I know that pub key. I've already, the pub key's been used. So given a public key P, find C, that should have been lowercase. Anyway, C, K, and I, such that the hash of C, K, and I times G plus K is P, right? If you look at that, that's, say C and I, squish them together, say like that's some message M, right? I've seen this before. This is the Taproot equation, right? You're basically trying to find a hash with the different pub key and a message times G plus that pub key that leads to the first pub key. And we know, I think there's a, I don't know, I've talked to enough people that like, yes, this is actually quantum secure. Despite looking very elliptic-y, the hash function makes it so that even if you have a discrete log oracle, you can't find arbitrary combinations of messages and keys that lead to a pub key. So that's kind of cool. I don't know if it really matters because we're sort of assuming that pub keys and private keys are now kind of equivalent in this world, but you can safely say, hey, I'm going to give you my unhardened public key derivation for my pub key, and that's something the quantum adversary doesn't know, and I can use that to prove my own knowledge of this and move my coins. So that's cool. Okay, so there's some downsides to this as well. Not everyone uses it, right? There's still wallets, I think, if you have a really old Bitcoin Core wallet that was initially made before deterministic keys, and you just keep using it, I think it keeps just making new private keys. Sometimes people share XPubs, so that's gross, and that's like a risk. And you got to do them all at once, right? So if you have a lot of UTX, so this doesn't sound that bad, but the fact is the people who are using address reuse sometimes tend to have like 10,000 outputs or something with the same key, and it's just like, oh god. So yeah, you got to do them all at once, and that's a little ugly. There's also zero knowledge proof way that people have talked about that does a similar thing. I kind of like this way better. I think it's a lot simpler. The zero knowledge proof does have an advantage of you don't have to do it all at once, and I think it keeps the doesn't reveal private key even in the hardened path. I don't think those actually matter that much, and I think the disadvantage is like much harder to verify to the point where it's like, is this really something that you could practically put into script verification in Bitcoin? I don't know. So I think this is maybe a little uglier but simpler way to do it. Okay, and then I have 15 minutes. Okay, distinguishing is another problem. So let's say you see a transaction. Does this require Lifeboat or Life Jacket? This is actually hard, right? I know, like I can look up, is this address, has it been reused? I can go on to like mempool.space. Sure, it's possible. You could make like a proof or something, but you don't want to have to run an address index, right? We know they exist. It's totally doable. You could make proofs, right? You could say, I can prove that this key has already been used, but that's like this weird like call and response fraud proof kind of thing. So an exclusion proof would be better, where you say, hey, I'm going to use Lifeboat. I can prove that my transactions, that my pub key has never been seen before. Okay. So maybe you could do some kind of exclusion proof based thing. A little weird. Inclusion proofs don't see them as helpful here. Now, the straightforward way to do it is you need an address index. And yeah, those exist. We've got a bunch of implementations, and you can run them today. But making that part of consensus is like, oof. So again, here, what I often work on is sub-kilobyte UTXO state roots, which that's all you need for validation, right? You can get it down to less than a kilobyte. And it's like, no. How about 100 gigs of an address index needed for validation? Oof. So hopefully there's better ways to do it. You don't actually need an index, right? You just need a set. And one of the things I'm looking at now is, a filter, right? False positives may not be the end of the world, right? So a filter of known pub keys would be something where, okay, if you're not in this filter, if you Bloom filter or some other type of filter, if you miss this filter, you can use Lifeboat. So you can use the easy path. And as far as I know, all these filter types, they have false positives but not false negatives. But they have a false positive, so it may be that you never reused addresses, and you're a good Bitcoin citizen, and you have new address for everything. But one of these still gets triggered by the filter as a false positive. And you're like, shoot, so I have to use Life Jacket instead. Maybe if that only happens 1 in 10,000, 1 in a million times, and you have some false positive rate that makes this filter really easy to use in consensus, maybe that's okay. Right, because you can still recover the coins, you just need to use a different way to do it. So this is one way. This is something I'm looking at. I don't have good numbers or answers for this yet. The other part of Life Jacket that I think is much messier is sort of this trolley problem. thing where, right? We're looking at this UTXO set, and we're like, well, that is an address reuse. You don't know if it's BIP32. You don't know if they used a brain wallet, right? Most did use BIP30. Like, there's not very many that didn't use anything. But there's some, right? We know there's some. And so it's sort of like, should people run this? Should this even be part of Bitcoin, right? Maybe it saves 99% of the coins, but destroys 1%. And those 99% would have been grabbed and stolen by the attacker. But also, we don't even know. Is it 99 and 1, or is it like 90 and 10? That's one of the things I really want to try to look at is like, when did these different techniques get incorporated into wallets and when transactions were happening and stuff? I think it's like the large majority, but try to get some better idea of range maybe helps with the trolley problem. But this is something we don't usually think about or work on in Bitcoin. Also, it's not just a trolley problem, because if a minority of the people pull the trolley lever, then the trolley splits into two parallel universes, and both groups get destroyed, right? So if you have a soft fork, which we may see next month, if you have a soft fork with minority enforcement, where you have a bunch of people saying, no, we need to run this life jacket thing. This is great. This saves 99%. And then you have a bunch of people saying, no, this is not Bitcoin, right? Like, you're not playing with people's money like this. If you have minority saying, let's do this, you may end up with two chains. And then in some chains, the funds are safe but need to be recovered, and some portion end up getting destroyed. In other chains, most gets stolen very, very quickly. It could be a mess. So again, potential reason a lot of people don't want to work on post-quantum stuff is the initial idea, I think, was decentralized, leaderless, deterministic cryptographic protocol, and it's like no, let's decide which coins live or die based on philosophical dilemmas. Different reason to work on this. Yeah, other methods. One thing people have talked about on the mailing list or delving is like make a sort of pre-commitment proof of a post-quantum key. So you say, like and it's sort of in a Merkle tree style, like open timestamps where, well, what if I do it today? What if I say, okay, here's all my different addresses today. I'm just going to make some, really simple, like this address corresponds with this post-quantum address. And I don't have to actually put that on chain directly. I can just put it in a Merkle path of some op return somewhere. And then later on, I can point to it and say, look, well, I have this proof. It's kind of like Lifeboat, LifeJaffe, but the proof is somewhere else, not inherent to my private key. I think that's really cool. It works, and it's very like low overhead. It's great. I think it's not on its own enough. Like, if people want to use it, cool. It's like real straightforward, real nice way to do it. But it's not reactive, right? It requires the users to like anticipate this and do something for the future problem. And I sort of feel like not that many people will, right? It's like, well, if you're worried about this, then, don't reuse addresses or start it to migrate to a shrinks address years beforehand. So I think that the real problem is most people won't, right? Most people will, and it's like a totally valid reason not to, where you're like, I bought Bitcoin because I want money that's not subject to theft or seizure. And I had my 12-word seed phrase, and I buried it in my backyard 20 years ago, and now I need to dig it up. And like, wait, I was supposed to do something? You don't want to like add requirements to hold on to your Bitcoin. It's really nice to be able to like bury something and then get it 20 years later. And this doesn't do that. But it's still a useful thing to have. I think it's cool. Okay, so I'm going to conclude. I guess I have a couple minutes for questions. Funds are Seifu, mostly. Post-quantum recovery is messy. Working to defend against attacks that never happen is the Bitcoin way. So I'm not saying, like, we need to do this right now. I think it's an interesting problem of, like, how we can find better techniques for this that people might be okay with. And then, code them. And then even code them with an activation trigger in the Bitcoin code base that hopefully will never trigger. But it's and then also, if it doesn't trigger but it's there, it may disincentivize people from triggering in the first place. Because I've seen companies, they're like, oh, we raised all this money, and they're like they don't say it, but they're like, yeah, we're working on a quantum computer so we can take all the Bitcoins, right? If you don't have the quantum computer, maybe, if you don't have the Bitcoins to steal, if you know that it won't work, maybe you don't do as much work on building the computer to take them, which is sort of like, a Lightning Network. Like, well, I'm not going to try to close the channel the wrong way because I know that all this software is there that will grab the coins from me. Yeah, so how do we do this? I'm writing options, not advice, right? I'm looking at like different ways you can do it. There's a link. I don't actually have anything there yet. I was going to, but it'll be there next week. And like these aren't live streamed, right? So it's like by the time the video's up, if people are watching the video, it'll be there. Cool. I think I have a couple minutes if we want to do questions, or if the next person. Okay. Thanks. Or if not.
Hey, any questions?
Or advice, or philosophical. No. Okay. Well.
Thank you.
Okay. Thanks.
Welcome, everyone. I'm, like I was introduced, I'm thunderbiscuit. I work on the Bitcoin development kit, mainly on the language bindings. So I'm a mobile developer myself, and so me and Matthew here, we basically handle all the language bindings for the Bitcoin development kit, which is primarily a Rust family of crates, and then this gets exposed to a bunch of languages that are used on mobile. And today, I'm talking about compact block filters, specifically for devs and users. So this talk is not really about the protocol. If you know anything about compact block filters or you've seen them on YouTube or whatever, there's a lot of talks and things written about compact block filters that are mostly about the mathematics and the statistics that make the filter work. And the BIPs also define this really well, but in the end, there's not a lot of use on mobile phones. So this is too bad, and I'm hoping to sort of promote that today. And yeah, so this talk is really about users. If you're a user of a Bitcoin wallet, you have a Bitcoin wallet in your pocket, and you're thinking, well, what would this do for me, right? You probably are using a wallet. Right now, if you have a mobile wallet in your phone, it probably does a sync through an Electrum server, which is like the standard in the industry. And compact block filters would be an alternative option that has different properties, and we want to talk about that from the perspective of users and for wallet devs as well. So if you're a wallet dev, you're in charge of a wallet, and you're thinking, could I ship this to my users? What would they gain? What would they lose? What's the trade there? There's a bunch of that. We focus on the users. What can you expect if you're a user? Should you make the request maybe to your favorite wallet? Hey, I'd love to have compact block filters. And then for devs, what does it mean? If you intend to ship this to users, what can you expect? And what can they expect? So we're going to go through how, and I have 45 minutes. Yep. We're going to go over how light wallets sync today. So we'll take a minute to talk about the standards in the industry right now. And then I will actually immediately break my promise of not making this talk about the protocol, and we're going to talk a little bit about the protocol and how that works and why that impacts basically what you can expect. And then I'm just going to run through the day-to-day sort of realities of having your sync sort of mechanism be a compact block filter mechanism instead of an Explora / Electrum / other technologies you could use for that. And then trade-offs that come with it, and gains. So you gain a lot, but you also trade a few things away. And then shipping this today, and in particular, I'll take a few minutes to talk about BDK for that. There's not a lot of implementations for compact block filters you could use, certainly not on mobile right now. I believe would be basically the only one. Maybe there's three, my understanding is there's three basic implementations. The Rust one maintained as part of the BDK org. There is a C# implementation that is shipped in Wasabi Wallet, and there's a third one. The initial one was called Neutrino, built by the LND team. So light wallets today. If you have a light wallet, if you have a wallet on your phone right now, the way this is currently done is you have some sort of loop probably that queries or pings the Electrum server once in a while to request history about specific transactions, specific addresses that the wallet watches, basically. You've revealed those addresses, the wallet is aware of them, and then it asks the Electrum server for it. This, of course, has a bunch of downsides that we know, namely the fact that you're revealing all your addresses to this Electrum server. It gets back to history. Yeah, I'm reading ahead of my slides. So this is fairly fast, and it's cheap on bandwidth, and you get mempool visibility. So these are like all good things in general, especially, and they'll come in handy as we talk about compact block filters and the way this impacts you if you transition from one to the other. It does have downsides, however, and we're going to take some time to talk about them. In most cases, your addresses are revealed to someone else's server. So that's really the core of the issue there, and a lot of the top wallets will actually offer you to connect to your own Electrum server. So your Blockstream Greens and Blue wallets and Phoenix even offers you to connect to your own Electrum server if you have one at home, but that implies, of course, you have some sort of Umbrel or Start9 or other sort of node at home that's running. That's a lot of hardware, uptime, all of that needs to be always on with an Electrum server. It's a lot of storage. Yada, 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 and it's not always on. If you have that, which I don't actually have numbers on that, I'd love to, if somebody knows the number of those, but it's, I assume, a very small percentage of people who can actually connect to their own Electrum servers, and so they get perfect privacy in that sense. Everybody else is relying on the Electrum server that comes with your wallet. So you hope that your green or your blue or your samurai or whoever else you're using, the wallet connects to a public server that doesn't log all of these things, because realistically the server can actually just, you're literally sending a big batch of scripts you're interested in. So like your whole transaction history is just like in one go revealed to this server, and it's revealed as it goes. So as you reveal more addresses, you actually reveal them to the server again. So like this server knows everything about all your addresses, the entire wallet, the history, everything about it. So this is the big downside. Either you run this yourself, so the way to mitigate this is either you run one yourself like we talked about, or you use one of the public versions. You can, in some instances, there's like websites where you can look up public Electrum servers and just hope against hope that they don't log anything about you or whatever, which is really too bad. And in most cases, on the big ones that have like good uptime, mempool.space has a public API, you can hit Blockstream as well, but you get rate limited on those super, super quickly. So it's they don't actually publish their limits, but I found through testing and our own wallets, like we found in general, that it's to the tune of like 1,000 addresses per hour, you get throttled right away. So you really can't use those correctly. So next up, compact block filters. We're going to talk about what compact block filters are a little bit. I want to get the feel for the room. Who here feels comfortable with the idea of compact block filters, has heard of them before? Okay, so good. So that's about half, and I want to make sure we bring everybody to speed rather, on the same, and we're on the same page. And this is not, I'm not trying to go into the specifics of it, but the gist of like how this works and why it works well. So every block on the Bitcoin blockchain can be reduced to this idea of this filter, and the filter is a small piece of data that's usually very small compared to the block it represents, and it tends to be, I have data on this, it's about 21, here's data on this. So if you think of like the eras of Taproot to now-ish, they are about 21 megabytes per 1,000 blocks. So that's a week worth of data of blocks, and that'd be about 20 megabytes you'd need to download for those filters. So each filter is on average 21 kilobyte. I have a GitHub repository under thunderbiscuit you can find called CBF data, which has a single Python script which will download all the filters for you. So be careful, because on mainnet that's many gigabytes, 12 gigabytes, and but then it has a bunch of SQL queries you can run against this data set. Gives you, all sorts of data on the filters. So that's fun. That's how I got that data. So the clients, those filters are basically a compact representation of what's in the block that might be interested for light wallets. So it'll be like the scripts that are in there, and the wallets can use that to decide rather if the scripts that it's interested in are potentially in this block. Now, this representation is not a one-to-one representation of the block. It has properties that allow it to be smaller than that if it was a one-for-one representation. And the way this is done is through like some math and stats that I haven't looked into, but roughly it allows the filter to be really, really small at the cost of actually sometimes producing, sorry, I'm jumping ahead a little bit, sometimes producing false positives. So it is possible to have a filter that will look like one of your scripts is actually in the block. You would download the block, and in the end, the block would not contain the script that you were interested in. So this is possible to happen. It's something like 1 every 700,000. So it's fairly rare, but if you monitor a lot of scripts, so if your wallets are really big, this will happen. And I have data on this a little bit later. But yeah, the filters are basically a representation of what you might be interested in. You get this filter, you can take a look at it, see, are any of my scripts in this block? If so, you just turn around, ask a different peer for the block, you receive the block, and then you can just feed it to whatever you need to feed it to update balances and whatever. Some of the cool parts about this, of course, is that it's plain Bitcoin peer-to-peer. So the nodes are serving these blocks. They're computing these blocks. They are, the filters, they are serving them. So there's no central server. You're not hitting some sort of API that is like a central point of failure. It's also, the uptime is really good because it's just a Bitcoin network. If a node goes down, your node is going to keep searching for more peers. And at the moment, I think I saw data, yeah, exactly. I saw data a few months ago. This was by Nick Johnson, a guy who works at 2140 in the Netherlands. He ran some sort of census, and it was on about 12,000 nodes, and around 10% of those signaled compact block filters. And this is a good time for me to also say, if you are running a node at home, you have a little, umbrella, you can turn this on at home. So it requires about 10, 15 gigabytes of storage extra because your node will need to compute the filters and keep them in storage. And then you can actually serve them. So this is helping everybody else who wants to sync using compact block filters, finding peers, and then finding peers that are close to them so the speed is better, all of that stuff. So, and I did it a few weeks ago for a node, and it just happened really quickly, and it was great. You get false positive, no false negatives, like we talked about. So there's no way for you to miss a block, so to miss a script. So if you're interested in 10 addresses, you download the filters. It's possible the filter looks like there is something in the block for you. You download it, there's nothing, but it's impossible for you to miss it. So for the filter to say there's nothing there, and in the end there was, so that's not actually possible. And lastly, I want to talk a little bit about compact block filters versus Bloom filters. If you're familiar with Bloom filters, I think it's BIP 37. So this would have been in the first edition of Mastering Bitcoin. If you read that, I didn't have the book, but I think this was explained in it. And back then, this was like the main light client technology. And the idea behind Bloom filters is that the wallet would compute a sort of obfuscated mask, I think it was called, which was a somewhat representation of the scripts it was interested in, and it would pass this on to a full node, and then it was the burden was on the full node to then check this Bloom filter against the blocks that it was receiving, and if anything was interesting, potentially to the light wallet, the node would then compute that and send the data to the light wallet. one of the downsides of this is that, of course, each light wallet would provide a different bloom filter to this node. So the nodes didn't have a very strong incentive to serve these bloom filters and like help people through that, because it's a lot of computation to do for the node, because it had to do for each of them was a different bloom filter. That's the first part. The second part is, I think over time it was found out that the privacy features we thought bloom filters provided were not as strong as initially thought. There's a lot of talks about that. And I think some of the old Chain Code Labs videos from, there's a one by John Newberry, which he explains why basically bloom filters are really not that great, or didn't have the features we thought they had. I invite you to watch this, but this idea of compact block filters turns this on its head, because instead of the light wallet telling the node what it might be interested in, the node computes this compact block filter on its own, and it's a deterministic process, so all the same block between all nodes will always produce the same filter. And so the node is just sitting on these filters. It has them in storage. It computes them once. If ever you want them, you request them to the node can just return them. It's free. It doesn't care. And so many peers can ask for those filters. It just has to return them every time. It's not extra computation from the point of view of the node. So it's a lot lighter work for the node to turn on and to serve, basically, people. It's also good from the perspective of the wallet users, because you can request many nodes about the filters. You can request the filters from different nodes, and they will all serve the exact filter. If you have one of your peers giving you filters not the same as the others, it's easy for you to download the block and actually compute the filter yourself. So you're going to see who amongst your peer is actually giving you false data. So this is all baked into this, the compact block filters. So this is my 5-minute run down of compact block filters and how they work. Now, next up, I want to talk about the daily grind. So if you want to do compact block filter syncing on your light wallets, what do you get? What does that look like for you? The first part is storage. How much is it going to cost you in storage? So if your mobile wallet, turns out you download initially a chain of headers, but this is all kept in memory. The compact block filters have a similar sort of header thing as the blocks do. So the headers are 32 bytes, and they commit to the previous header hash as well as the data inside the filter. You download those. This is held in memory. And then the filters, same thing, are not persisted. So you download the filters, you check if they match against any of your scripts, and you can discard them if they don't, or even if they do once you've downloaded the block. So storage, 0. I should preface here that I'm actually, in this case, talking about the Kyoto. So Kyoto is the library that is developed in Rust as part of the work on Bitcoin Development Kit, and 2140 actually, which is supporting Rob, the guy working on this. So it's possible there's like different implementation that would do slightly different, but roughly I think they would give you similar properties. But the one I'm most familiar with is the one in Rust. The bandwidth is where it gets a little bit spicy. So we want to know what's up with bandwidth. Bandwidth, in this case, for compact block filters, I have a few examples here to sort of give you ideas. A few weeks of history and a handful of transactions is 100 megabyte. That's totally decent. The big bandwidth requirements happen at the recovery layer. So on the time, and again, this is a one-time cost, but if you recover a wallet that goes back in time, right, you're like, oh, this wallet is like 3 years old, you're going to need to download all filters and then check them all. Again, you don't store them, but it is bandwidth requirement. And in the worst case scenario on mainnet from Genesis, this would be 12 gigabytes. So it's not nothing. You don't want to do this on data, maybe, or while you're in the bus. But also, it's not that bad. Because, for example, I looked up the size of a Netflix movie on high definition on your TV, and it's about 14 gigabytes. So that gives you an idea. This can be done on your nightside table when you go to bed. It takes about half an hour, whatever. Of course, this depends on your internet speed, but yeah. Much more like, and this would be for Genesis, which is kind of ridiculous. Like nobody would sync a a wallet from Genesis, or I mean, very, very rare that this would happen. Most likely, if it's a wallet you're recovering from, a year's worth of block, would be a gigabyte. It happens in a minute or two. And then since Taproot, how old is Taproot? Like 4 years or something? So that'd be 5. So again, nothing too bad. And this would be done pretty quickly. One caveat here is that this is for filters, and you also need to download the blocks that you're interested in. So if your wallet happens to be like very, very heavy, like it had a lot of transactions, you end up downloading a lot of blocks. Plus, of course, all your false positives. False positives are not too bad. I counted some data yesterday just to give us a rough estimate, but if you had a wallet that was monitoring 200 addresses, so a decent amount of, addresses, decent sized wallet, you would get 25 false positive blocks over 100,000 blocks. So this is 2 years worth of data. You would end up downloading 25 blocks that were not required. So this is, 100 megabytes that are just false positives. All other blocks are required, and then your wallets can just use them and do everything it needs. I'm going a bit fast, sorry. Sync time, next up. So how long is that going to take me to sync? I'm used to my Electrum wallet. It's, instant, whatever. How is that going to cost me? Year gap. So if you haven't opened your wallet in a year, it hasn't been touched, on Wi-Fi with a fast peer, 1 or 2 minutes. The speed of your peers does matter here a little bit. So in our case, Kyoto will try to find a bunch of peers and pick the fastest one to download your blocks from. Even on the slow peer, you're just doubling your time there. It's not too bad, but still, at that point, this is something you definitely, if you're a wallet dev here in the room, this is something you'd want to go through, like UI and UX. You want to make sure that users are aware that this is happening. A few months of gap, 10 to 30 seconds. A week is a moment. This is near instant. You don't even, same thing with daily use. You don't even see it's happening. It's basically like boot time of the wallet. It's already synced up. So all good. Lastly, for this, I want to mention that I think a typical way that you can deal with this and ensure that the wallet syncs are fairly quick is by enabling background syncs, and the iOS and Android operating system give you hooks for that sort of thing, where you can request that tasks like this can be performed on things like you want to say please, when I'm on Wi-Fi and I'm plugged in and it's middle of the night, say, for example, and then you would perform that background sync. If you do this for all your wallets, so this would be a week's worth, say you do it on Sunday night, this would be about 20 megabytes. So again, it'll be completed in 3 to 10 seconds, and then on anytime the user opens their wallet, they'll be up to speed. It'll basically be instant. So that's great. Gains over Electrum. So yeah, I want to sort of wrap this up here in this case, because we've talked about what it looks like, but what do you gain compared to your standard, maybe Explora or Electrum wallet? The first and foremost, the big one is the privacy aspects. So your addresses never leave your device. This is, I don't know if I've stressed this enough, but your client, your mobile phone, becomes a node. It's just a peer on this peer-to-peer network. It has peers, it communicates with them, and it'll just ask for those filters. And whenever a filter matches against scripts it's interested in, it'll just request a block to a different peer, and then update everything it needs. And so you never actually disclose your addresses to anyone. Everything happens on device. Your peers only know that you are requesting blocks, you're requesting filters, and then the way this is done for us in Kyoto is that the blocks that you're interested in get sort of queued up until you're ready to go, and then you start downloading them, but you download them from random peers, so it's not even that all the blocks you're asking are coming from the same peer, they're all just randomized, and you can harden that even more by adding decoy blocks, where like and that would cost you a little bit of bandwidth, but you can end up downloading, half of your blocks are true blocks you're interested in, the other half are blocks you're completely decoy. So like the nodes are just completely oblivious. They can't really know what's happening. At least it's a high level of privacy there. You have super good reliability for this, right? No rate limits, no server downtime. The network is always on. That's one of the big properties, of course, of Bitcoin. So you get that for free. You are independent, so there's no infrastructure for you to run. Trust, you don't have to have some sort of, DigitalOcean droplet with an Electrum server or something at home, and then it goes down, anything like that. It's always on, always ready. You don't need to trust that the hardware is, working and everything is going well. And lastly, you get near instant notification, because depending on the wallet you're using, there's just like a big breadth of solutions there for syncing. But most typical wallets will do some sort of like loop where they query the Electrum server every few seconds to know if anything's happened. So it's kind of like always polling. And so if you're in the middle of that loop, you would know. Some other wallets do it more like behavior. So like on particular navigations to certain screens, it'll do a sync, or when you send a transaction, or there's a button to sync, literally. And so, but anything else in between the loops, depending on the time of the loops or whatever, you end up with not knowing what's going on. Whereas in this case, you get it instantly because your node has appeared on the network, it receives the block, and boom, you're good to go. Now I'm selling this hard, hopefully, like at this point. There's a bunch of like really cool stuff. I hope I'm communicating this well. There are some trade-offs, however, so I do want to talk about that, and because mostly I think those trade-offs are in many cases worth it, but it's important for the users to know, and it's important for the devs to know them as well. The first one and the biggest one, as compared to your standard wallet, is you don't get mempool visibility. So your node is not aware of the mempool. It does not keep, it's not realistic on the phone, for example, to expect that you would keep track of the mempool. And the filters are not calculated for mempool data, because that wouldn't make any sense. Each node has a different view of the mempool. It would have different filters. Those filters would need to be recomputed any time a transaction comes in or comes out, so it doesn't make sense to actually have filters for the mempool. So your wallet only sees transactions when they're mined. That's kind of what it is. If you're familiar, or if you're used to your standard Explorer Electrum wallets that show you incoming transactions because it picks them up from the mempool, this is something your users will miss / open a ticket for. It's like, what's going on? I don't see my transaction in the mempool. That's what it is. There's ways to go around that, and I'm sure you can start thinking about that. And everybody has ideas, and we've seen sort of like you could certainly do some sort of hybrid thing, or sometimes people are specifically expecting payments, right? Like somebody's in front of you and they're sending money, or you're expecting payment at a specific address, so you could use alternative options. But in the standard sort of clean compact block filter case, you would not have any mempool visibility. So no pending, and yeah, this is the biggest downside. Next up, our fee estimation. So and this is connected to this idea that the node doesn't know anything about the mempool, you don't really have good fee estimation. So that's another slight downside of this. You have no way to get really clean, easy fee estimation just from the compact block filter node. If you want fee estimation, there's like tons of ways to go around this. Of course, maybe the first one that you could reach for is this idea of the average block fee rate, where like you can actually download the entire, like you can ask the node for the chain tip, get the entire block, see the Coinbase output, remove the subsidy, so you'll know how many fees were paid in total for the block, divide that by the weight of that block, and then you'll get an average fee rate for this block. This is actually not a bad way to go about it at all. I ran this a few days ago, I think, and you're getting ideas on the latest, like 3.26, 2.10, 497. And this would be a way where you would not require any API, anything else. This is fairly approximate, but you have no server dependency. It's pretty cool. The downside of that is you might end up overshooting. So if your users were using straight up the average, and then at that point that becomes more of a UI, UX problem where you need to communicate that correctly to the users, and how are they going to choose and overshoot, undershoot, that sort of stuff. And then, of course, you can actually hit publicly available servers for this, and they return really accurate and really precise data, which is not a bad way to do it. Either it has nothing to do with your transactions, you're just requesting fee rates, but if you wanted to keep it pure, then you wouldn't have access to that. My third trade-off for using compact block filters on mobile phones is user education. So it's related to what I've been talking about, but in general, your users don't really know or understand compact block filters really well. So you have a bit of a journey there. If you want to ship it as an alternative sync mechanism for your wallets, you'd need to make sure they really understand well what they gain out of it and what they lose out of it. So, for example, the payments that appear after confirmation, or the fact that if they are recovering a really old wallet or a wallet that has a lot of activity, then they probably want to do this on Wi-Fi at home, kind of thing. Depending on the age of the wallet as well. And then there's a bit of question there also, like the users in most cases don't really know how old their wallets are. Like even if you ask, it's like, what block was your wallet created? Of course, people don't know. So you want to be conservative. So you probably want to go a little deeper than you would otherwise. And of course, on the worst case, you end up syncing from Genesis, and that would be 12 gigabytes you would need. What they gain versus what they pay. And my advice here would be to design around it and lean into it, because it has such beautiful properties on one side that it's worth like explaining them well, and then potentially having people understand why it's worth paying that cost to gain these properties. And trade-off number 4, this applies mostly on the Rust implementation right now, but we see a lot of wallets. If you're familiar with like the typical wallets, like they often, the piece of software, the wallet supports a lot of wallets, right? You'll have like many wallets supported in one. And at the moment, a single instance of this compact block filter node can only serve one wallet. So if you're doing this background sync once a week and you need to download 20 megabytes of data for the week, and your user has like 6 wallets on their mobile device, then that would happen 6 times in a row. So it's one of those, but this is actually actively being discussed, and we have 2 different competing ideas there that can potentially help solve that, where you would do it once and then update all wallets with it. So this would mitigate that. I have 15 minutes left. Wallet developers, next part's for you. Shipping this today. Can you do this? How does this work? BDK Kyoto, Bitcoin Dev Kit. I'm plugging in the the stuff. We are ready for you. If you are interested in this, Kyoto is the name of the project maintained by Rustacean Rob, and he is basically this is super active. So and there's a few users in production right now. So including researchers at 2140 that are using this. You can use it right now. You can download it. You can use it for the hackathon. You have an hour and 15 minutes to build a hackathon around this. Launch your agents on this. BDK, of course, handles the wallet. So Kyoto, and the other cool thing about Kyoto is that it is a fully standalone thing. It's not part of like just inside of BDK. It's a standalone thing. You can run it and use it with different wallets if you want, as long as it connects, or if they need blocks or anything like that. So it can handle, as long as you can give it scripts, it will return blocks, basically. That's the input-output that happens there. So you can use it on any other wallets. If you're interested in, of course, the BDK family of wallets and libraries, then we have a bridge crate that will allow it to work super well together. It's seamless. And we have this in production today. We have bindings BDK's bindings for mobile, so Swift, Kotlin for Android and iOS, Flutter, React Native, Kotlin server-side, Java, name it. We have it for you. And we maintain 2 sample applications that you can use on, and you can use compact block filters today for them. The iOS version, if I'm not mistaken, is on test flight. Is that correct? Is on test flight. So if you're in the room, the Wi-Fi is not that great, but if you trigger it for Signet, I think Matthew did it yesterday in like, I don't know, it was less than a minute, yeah. So that's great. The Android version as well is maintained by me, and it's on a repo called the DevKit wallet. Same thing. You can get this working in a minute, and this works reg test, Signet, testnet 3, testnet 4, all of it, just CBF. What would your integration look like if you if you want to do this? You basically just wire Kyoto, and it'll be a main source for your BDK wallet. If you want to use it outside BDK, like I said, you just have to have a way to basically handle. You get scripts, it returns blocks. That's how it works. You feed it, yeah, there you go, and you apply your updates as they arrive. You're going to need to make a few decisions. If you're interested into implementing this for your users or people watching this video, I think we'll hit YouTube at some point. Things like sync from birthday versus full recovery scans. I know there are BIPs on wallet recovery data, like 139, I forget. There's like a few maybe that are competing for like that sort of metadata. This is the kind of thing that would help those kinds of recovery, reducing the bandwidth. Again, the bandwidth for those is just a one-time cost. If you're on Wi-Fi, it's not that bad. Peer selection, how many connections you're looking for, how many connections you want to maintain, that sort of stuff. And the background sync, scheduling, and then often, at the moment at least, because everybody's using the Electrum protocols, then protocol, you need to think about like fallback or offering the option of one versus the other, or a mix of the two, or anything like that. So these are some of the decisions you'll need to make. And finally, is this production ready? And yes, of course it is. And I'm here to tell you that it absolutely is production ready. Come and use it. We're merging new stuff all the time. There was a version released yesterday, 0.6.3, I think, for Kyoto. So it's like very, very active. And yeah, so come give us your feedback. Try it in the hackathon. This is the perfect time for this. Yep. Peer availability is sufficient. It's decentralized. We have good peer availability. We haven't had problems at all finding peers. It's been great for the past few months. And yeah, there's a lot of UX work that needs to happen. And this is my last slide, takeaways. What I hope you get out of this talk. The first one is that this, in my understanding at least, certainly the big trade for compact block filters versus Electrum is that you trade mempool visibility, which is the biggest downside, for really, really good privacy for the wallets, as compared to a public Electrum server. If you have your own Electrum server, of course, you don't have a problem with that, but yeah. The numbers work. No storage, seconds for daily sync. This is really good stuff. And then the background sync. And you can ship this today. And lastly, it's probably a good option for some users. So that's what I hope you get out of this talk. There's a lot of users for which this trade-off would be is fantastic. If you told me I would totally turn it on my wallets. And but there are some for which it might not be. So the idea of offering both is probably great at this point. And yeah, hopefully we see a lot of use. And of course, if you are a node operator, I invite you to turn on compact block filters for your node. It's, I think, 2 flags. So you need to like make sure the node actually computes the compact block filters, and then there's another flag for actually serving them. So those are the 2 flags you need to turn on. They're easy to do on most of the big node, little hardware implementation that people have at home. And that's it. That's my talk. Thank you very much.
Is there any question?
Yeah, you said there were no false negatives. Can you say something about a server that occasionally lies about the compact block filter it returns and what the deal with that is?
Mm-hmm. Yeah. So there's a few ways that the nodes could lie to you, for example, by giving you a false filter. So the way this is done for Kyoto is that you download this chain of headers that are associated with the block, the best block. So you get the chain tip, and then you download all the chain of headers, and they will be, of course, committing to each other. And so you end up with this chain of headers that matches your block tip, and then you can get this from a few different peers, and then therefore to lie to you, you'd need to have like a series of peers that are like all colluding to give you the false filter and give you the same filter. So that's the first thing. And then if you do have any discrepancy, you can actually ask for the block. You get the block, you compute the filter yourself, and then you figure out if this node is lying to you. And in some cases, actually, and Kyoto has sort of like contingencies for this, where if you have a sort of fork, you can download both and then decide which one is the true one or the chain you want to follow for the most work, and then you go that way. Yes, sorry, the filter headers or the... Yes, yeah. So the filter headers commit to the previous filter header and the filter itself. So that's a hash, it's a 30-byte, yeah. And so you end up knowing that the filter header is representative of the filter, and then if the filter is representative of the block, then... No. Yeah, you need to make sure that you're on the tip that you believe is true. Yeah, in that sense, yeah. If you were on the wrong chain, you would, and then you're at the edge of my knowledge for those special cases, so I apologize for that. But yeah, I don't know exactly how that gets resolved. Yeah, maybe it's dependent on the implementation too. I know that for Kyoto, it'll be like asking a bunch of peers, verifying them against each other, and then yeah. That's one of the beauties of it, is that this filter is like computable by you, so you can. It's hard to lie to you unless all your peers lie in the same way. It's very difficult to get lied to.
Another question.
Yep.
I'm using BIP 158. I actually didn't know about Kyoto. I boycotted a solution on WASM and HTTPS for my own server, and
Nice.
It's something that I'm noticing is, are you considering putting dummy data? Because eventually some IPs are going to know which blocks did you pull. Are you considering also to inject dummy blocks or blocks that are not within that, so that at least if somebody's looking at your download, you have the extras?
Yeah, exactly. So this is, I mentioned that a bit earlier, but this is one way you can harden the way you're sort of like making sure the nodes don't really understand what's happening. First of all, if you have many peers and the blocks you need, you randomize who you're asking which blocks for. So that's the first thing you do. And then the second thing is you can add a bunch of dummy blocks. And this would be, in theory, just a parameter on some method, right? You could have 90% of your blocks be dummy blocks, and 10% be the true blocks you're interested in. You could be 50-50, it could be anything else. But yeah, so that would give you. But also the fact that you're requesting these blocks from random peers also prevents them from colluding against you. Like it would be very hard to get a real true picture of all the blocks you're interested in if you are requesting them from different peers. So yeah. And you can, of course, rotate your peers and all that stuff. So that's another thing. Yeah.
Anyone else? No? So thank you, thunderbiscuit.
Hey, I'm Andrew Toth. I've been contributing to Bitcoin Core for a number of years now. I'm sponsored by OpenSats, and I work for Exodus as well.
Very cool. And what part of the Bitcoin Core code base do you work on?
I'm primarily focused on the caching and indexes, just trying to make things more performant, use less resources so that more people can use it on different types of hardware.
Okay, and tell me, I heard a rumor recently that you saved Bitcoin. You saved Bitcoin on IBD. What is that about?
So during the ordinals boom, there's a lot of new UTXOs being created. So between blocks 800,000, 900,000, there's all these UTXOs that cause IBD speed to diminish, right, to get slower. And recently in Bitcoin Core, that'll be released in version 32, we released a new speed up that more efficiently reads all these UTXOs so they can validate blocks a lot faster. So syncing time is going to be even faster than before the ordinals era. So anyone who's concerned about the speed impact of that should no longer be worried.
So you're saying that now, in Bitcoin Core version 32, IBD will be faster than before, even when there was an ordinals at all?
That's accurate, yes.
Let's hear some numbers. Can you give me some, how long can I expect an IBD to take?
So on your laptop, under 5 hours. On a Raspberry Pi, under 12 hours. And if you were running it in AWS, like network connected storage, it would take several days. Now you can do it in about 12 hours.
That means we don't need to do a soft fork to eliminate spam anymore.
That's out of scope for what I'm working on. I can't speak to that.
Okay, that's really cool. I want to ask you a little bit more about how this optimization works. When we spoke about this before briefly, I understand you mentioned that before the validation of the blocks, the transactions happen in sequence, and then now you're parallelizing it. Is that accurate?
That's right. So every time a UTXO has to be validated in a block, so let's first say, so like every block has transactions, and each transaction has inputs that they reference UTXOs. And so since there's a lot more UTXOs, these UTXOs have to be looked up from disk, and that can take a long time. And previously to this change, for every input, we would do a sequential lookup, and all that time looking up was time that was wasted and couldn't be spent validating. So now we parallelize this lookup and look up many more UTXOs at the same time, which removes that waiting.
You're looking up many UTXOs at the same time during the IBD process.
For each block, yes, that's correct.
And maybe something that you can clarify. I understand that IBD happens in a couple of distinct phases. Can you give me like a sequential breakdown about how IBD actually happens from when I first turn on my node?
So with default settings, you will first sync the headers chain. So you will connect to peers and get their best blocks and sync all the block headers from Genesis to the latest block. And once your node is satisfied with the headers, you begin requesting all those blocks that the headers correspond to. And this first sequence, though, is by default assumed valid. So what that means is every block that you are validating, we assume that every UTXO is being spent validly, as in the signatures are correct. So we don't validate any signatures, and that speeds up IBD as well. You can configure your node not to have assumed valid if you're paranoid, but once you get to the assumed valid block, which is configured in your node, any blocks after that will have all their signatures checked. So that's the next phase, which is syncing all the way to tip.
We're assuming that a particular block is valid up to a certain point.
This height is hard-coded into each release of Bitcoin Core. So before a release of Bitcoin Core goes out, the Bitcoin Core developers look at one of the recent blocks and verify that that is part of the best chain, has about 2 weeks of work on it, and encode that into the code base. And then so when your node starts with that release, any block before that, by default, will be assumed to be valid and won't have signatures checked.
Okay, so what's the difference between the amount of verification you're doing on a block that's assumed to be valid versus not?
What's the amount of verification? So if you have an assumed valid block, you are still going to go through every input and make sure that the UTXOs exist. And so you can't double spend or spend coins that don't exist, but you won't check that those UTXOs have a valid signature. So we assume that they're not being forged. So if a block is being validated without assumed valid, then we look up each UTXO and make sure they don't exist. But then we also ensure that the UTXOs are being spent within the consensus rules. So we execute the script and verify all the signatures of those UTXOs being spent as well.
Interesting. And this is a specific feature of your PR that was merged?
The assume valid feature is not something that I worked on. This was the feature of reading inputs in parallel, which is what I worked on. Yeah.
So your work is specifically on the parallelization inputs. Verifying inputs in parallel.
I've done several different caching improvements. This is the latest one, though, that's specifically about caching improvements.
Okay, very good. So now you've saved Bitcoin IBD. Very good. What are your next tasks that you're working on? What are the next things that you're looking forward to that you think are the most important?
So right now, using Bitcoin Core with a transaction index has a very large storage requirement. So it's no longer really feasible to run a TX index node on a 1 terabyte or lower disk drive. So one of the things I'm working on is to shrink the disk space required for a TX index, and then also allow it to be run in prune mode. So in prune mode, you can prune blocks that you're not interested in anymore and reduce the disk space considerably.
Okay, and what would be different about that compared to, because today we have prune nodes. What is different about what you want to do?
So you can prune your node, but then you can't look up any transaction by its TXID inside the blockchain unless you have the block hash. So that's one of the reasons people run TX index. And another thing I'm looking into is adding an address index as well. So then you can look up your history on a prune node. So you can have basically a personal block explorer on a prune node running in much less space than is currently required. Because if you want to run an address index today, you need an unpruned node, and you also need a TX index, and you need to also run Electris or another indexer on top of that. And that's not really feasible for a laptop today. So this is going to really shrink the requirements needed to be able to do that.
Cool. And your talk here, so you're going to give the talk tomorrow. What is the main theme of your talk? What are the main
theme of the talk tomorrow is going to be about this work we did for parallelizing the input fetching to increase sync speed, and I'm also going to touch on the index improvements that are in progress.
Thank you, Andrew.
Thank you.
I've got open stays.
Open stays. Okay, cool.
So booking platforms have a consensus problem. So basically when you're having or running an Airbnb, a campground, whatever, they're kind of all centralized platforms. So the consensus problem in Angle is you've got the guests, the property, payment rails, notifications between the customer and the property owner, and then the channels. So you can have your own system, but of course you want to be on Airbnb and Booking and VRBO and whatever else. So the system basically brings all of those together. When a guest registers, you're going to have golden timestamps hashed with their privacy information removed, and then the wavelength. Once a person goes through, does their booking, gets rewarded 1,000 cents. Let's see if it works. So, pretend you're a guest. Maybe we're in Toronto. You're looking for a place to stay. Consensus Commons. Maybe you want to stay in the node room. And here's kind of what a customer would see. So you get to pick your dates, all that fun stuff. There's the price, 19 cents plus 2 cents for HST. It makes our beautiful 21 number. If you want to check out the place, hot links to a whole bunch of things that are amenities. But let's try booking something for tonight. So you'll put in your information, your phone number, continue to payment. And when you're paying, you have the choice of Bitcoin or fiat via Zaprite and their API calls, or if it works, paying with a Signet wavelength wallet. So let's try the wavelength. And of course it's broken. There it is. Okay. You would put in the same booking email that you just booked with, request an invoice. So this is using Signet sets. You would be able to scan that, pay that, and once you kind of pay that, it was working earlier. So it makes an in-browser wallet on the fly with wavelengths, which was working earlier. So I just will skip out.
I feel you, bro. I feel it.
Yeah. So let's just do the Zaprite kind of thing. That's cool. Just lock all that. Let's do some test that. There's booking confirmation. Payment confirmed for the Consensus Commons.
So, welcome to Is This Good for Bitcoin? Just Ask the Bips. So we're trying to solve a very simple problem. We're trying to make information about exchanges in Bitcoin available to non-technical persons by taking the Bips as the only source of truth, so unbiased information. And for that, we use Shakespeare to build the whole application and UI. And so Tuma is gonna demo you one of our features to check that.
As Hugo said, we took the BIP repository, only source of truth, we created a local database, all the bips with all the information about the bips, and we present them as only the consensus bips. So what's about the software? So for example, we have consensus cleanup, we have so on, and they are divided, as you can see, in deployed, completed, which means ready but not deployed, draft, closed. So we have all the states, the different VIPs. When you look at the VIP, for example, let's look at the consensus cleanup, you will have the possibility to actually read the VIP itself. So you have this window in which you can see everything technical, the technical gibberish. But if you're not technical enough, you will have a small help. You will have this ask about it, and the LLM will take the VIP itself, and it will condense it in a very simple explanation so that even a technical person would be able to understand. As a final step, we are also creating a sentiment on the VIP itself, and Miguel will talk about this.
So once the person understands what is the change, we also want to tell them like, hey, this is how the network is perceiving that change. And for that, we are assessing the nostr relays to see how many subs for or against, just as a first phase, but also to have at the LLM categorize how everybody is thinking about for get the person to understand if this is a good change for
So let's see if you have a question.
How did you guys feel about gamable, like anyone could like
everything on bit 110?
Of course.
So from the nostr relays,
45, yeah.
Seems slightly positive. Yeah.
seems like it could be anyone wants to spin up an Oster account.
What we're thinking too is that with more time we can open up also the sources, not only for Nostr, but also all different places, so that we can provide an internet thing, like what is happening.
And also the zaps tell usually put your money where your mouth is, which means if a lot of people are zapping many money to like, yeah, let's go big 110, it means that there is some support, at least the people are very vocal about this too. So that's
to add to that, on the websites, so once a non-technical person read more about like consensus change and the specific BIP, then he's going to be able to vote with sats, like 10 sats to vote for or against after he's
yeah.
Makes sense with my
All right, so welcome to Node Signal. It's Signal for nodes, essentially, hence the name. I thought of it because I'm researching Bitcoin Core versus Bitcoin Knots. So the first thing you result when you kind of dig into that is, man, I really wish there was a nice, organized way to discuss consensus in a nice, efficient, and healthy way. And what better to do that than with the Bitcoin blockchain itself? So what this is essentially is just using your peers, connects to your peers that you have on your Bitcoin node, and allows it to be a social media platform. So it links to whenever you have your node software on, whether it be Windows or Linux, and you can hover over your connections. They're distanced by latency, and it's all this nice little cool little web map. Shows the implementation, what they're signaling for, and all this other cool stuff. And you can go to your messages here, and you can look at the messages for that's little encrypted pin and all, and like nice little AI generated messages here, and I think it's really cool because like I've always wanted to be able to like talk to my peers where I see like my actual peers. If I scroll up here, this is my actual mining pool that I vibe coded earlier. This is not part of my project, but just for an example, my peers went up by 1. It'd be really cool to message that guy that just joined. So I always thought that was cool, and I thought that this would be a really interesting way to do that. And you know, it's a cute example and all, like, oh, this is all just like these are all fake nodes, but I'm happy to see that this actually does connect to the Bitcoin blockchain. And I can put my actual node here and put a nice little pin to 2013 again, just for simplicity. I can add it and bang. So that now that actual thick line and that little live indicator showing that actually is my connection. So, and I might lose points for this for some of the people who might not agree with me, but this node is Bitcoin Knots, and it does say it detects that it's signaling for BIP110 user activated soft fork, and it gets that all from just that code information there. So it actually will show you like what you're signaling for, like what you believe in, and then now you can message this person and say, you know what, BIP110 actually stakes, and send it. And obviously it says there that they don't have it installed yet because I slacked off and didn't do that part yet and installed it on my node. It's all the way in Alabama. Fortunately, I was not able to do that in 24 hours in the afternoon. But yeah, that's pretty much my whole project right there.
Oh.
How much this did you actually do today?
Today, this was 100% in the last 24 hours. I started it last night. I thought I wasn't really sure what for the topic of consensus, how this would actually go and what I actually wanted to do. But I want to have it somewhat related to my research with Bitcoin Policy Institute. So I thought this would be a great way to do that. So yeah.
Bull Bitcoin player.
No, so Bull Bitcoin is a wallet.
Yeah.
I'm one of the contributors of Bull Bitcoin wallet.
Okay.
And we are using BDK, so Bitcoin Development Kit bindings in Dart and Flutter because our application is for Android, iOS, and it's coded in Flutter.
Yeah.
So the bindings are related to the conference, the talks that was given by the BDK team yesterday.
Right.
Today they presented the compact block filters, so CBF, to improve the privacy of the users. And I wanted to attempt to integrate it in Bull Bitcoin. So here is my demo. So basically, this is a website where you can fetch the code of Bull Bitcoin because everything is open source. This is my profile because I'm one of the contributors that you can see here. And this is my demo. So my demo is just a debug APK that I built recently. You have a wizard when you start the Bull wallet, where you can decide the themes, the language, the currency, okay? Basic stuff. You can decide to help us with some reports about the errors that you experiment. And here I added this new screen that offer to the user to enable the compact block filters for privacy gains. I wouldn't turn on by default because it has some drawbacks. Basically, you will see once we import the mnemonic into the wallet, you will have to wait to synchronize from the peers on the network the block filters. So we will see now. We will recover a wallet. So I will use a dummy seed, the famous zoo. I'm really used to this one. And wrong. Okay, so now we will have this new page that will try to synchronize the compact block filters, as you can see here. So the first step is it will attempt to find some peers on the network, so nodes. And then we will see a new bar under that will try to fetch the block headers. So then it will download, you see here, it started to, wait, you will see, yeah, now you see the number is changing. So it's fetching the block headers. Once we will have all the block headers, we will try to download the block filters. So this step is super long and bad for presentation at a hackathon because there is 12 gigabytes to download. So I can't show you at the end what is happening, but basically you can sync your wallet in a more private way than relying on someone else Electrum server, basically. As we do now in Bull, you can set up your own Electrum server, or you can use Bull Electrum server, but you can also use with Tor. The issue with that is when you use Tor, your IP is changed only once per 10 minutes, right? So when you do a sync, you actually give a batch of addresses that can be used against you to cluster you, right? So these block filters are very important to give you an alternative way of syncing your data without risking to expose your addresses. Basically.
I see. So that's the so compact block filters integrated in the app. You can use that to be able to receive your blockchain data without giving away all of the addresses.
Yes.
Okay, cool. Right.
So the challenge was to try to implement it very fast, but I faced a lot of problems because, for example, if I lock the screen like this morning, it was restarting the sync from zero and stuff like this, and I don't have 12 gigabyte of 5G right now. So
yeah, fair enough.
It's not. I don't think it's the best to showcase in a hackathon, but I think it's really important, and I think there is a large consensus on the privacy. And these kind of techniques are really important for the users. So that's why I'm interested to bring it to Bull and make it.
I'm wondering, for the title, the project name. What's your project name?
My project name is just compact block filters in Bull.
Okay.
I think it's something like that. Yeah.
Yeah, so the project we came up with here is BitFox. It's a Bitcoin-backed poll system that's tied to Nostr. And so there's kind of two things people can do. They can create polls and cast votes. And the way that it's Bitcoin-backed is that you effectively send a transaction to yourself that's time-locked for a certain amount of period. That's based on what the what the poll creator designated to show that you allocated some Bitcoin for this poll. So just go through poll creation quickly.
So this is what it would look like for the author of the poll when they're making the customizations to set it up.
Yeah. So after you've logged in already with your Nostr account, then you can create a poll. And what this ends up doing is just creates a Nostr note for this poll. You decide how much Bitcoin people need to lock up, and whether you want to allow them to do it on-chain or Lightning, or focus, or narrow it only to just one option. And then you choose a timeline, and then you create the votes, create the poll. So we already have a couple created so far. So for example, this is one of the polls created. So just to create one quickly, vote me, and then we just say option A, option B, and then let's say it's 1,000 sats, either on-chain or Lightning.
And let's set the start date as today.
Yeah, so for today, at noon.
Yep.
And then voting ends, let's say tomorrow at 1 p.m. And then the deposit lockup could be the same as the voting end date, or it could be a bit longer if
the author chooses so.
Yeah. So it could be just tomorrow at 2 p.m.
That works.
2 a.m. Oh, and so since that's 2 a.m., it has to be earlier.
2
that's
p.m.
too early,
works.
so it needs to be 2 p.m. Great. So that creates a poll. So this is for poll called Vote 23. And so to cast a vote on this poll, you pick A or B, and then you have to choose whether you want to lock up your Bitcoin on-chain or via Lightning. So this is still, it's at a proof concept, so this is not actually implemented on the back end yet, but we would use Wavelength for the Lightning integration and Bitcoin Dev Kit for the on-chain checking. And then that's possible. And yeah, React Native is the UI framework. So
Cool. So do people actually need to lock up their Bitcoin, and it needs to stay locked for the period of the poll? That's exactly right. They need to have a minimum amount there in order for their vote to count. Of course, they can withdraw at their discretion. However, if they withdraw for the ending of the poll, then the vote will not count. So they should fit for that duration that was set by the poll. Does the votes get in, if you put in more Bitcoin, do you get more votes, or is it one vote? One vote per person. Okay.
Two questions. With regard to timing, you use block number to basically estimate when the beginning and the end. And the other question is, how do you handle online transactions?
So for online transactions, that's why the on-chain option is, maybe you don't always want to use it. That's why Lightning would be better, because the on-chain, it's hard to say how it works. So this is more proof of concept at this point. So those are some good things we'd have to work out.
Okay, and the timing is an estimation of the block height.
Yeah, so timing is probably just based on date. So date time, not based on block height. But
So it could be set to 4 hours, 48 hours, a whole week.
Yeah. Okay, thanks.
Go. Okay, so I don't know if y'all have ever interacted with security proofs. But if you go to Claude and you say, hey, Claude, why is a stream cipher secure if the pseudorandomness is good? You will get an output that looks something like this. We've got some dense definitions with a bunch of notation. We've got some pseudocode that we don't really understand what it is doing, what it has to do with anything. We have some theorem, and it talks about reductions, and then some inequalities, and then at the end it says we won. Great, that sucked. let's try something else. So say that you're trying to learn about cryptography and you want to actually understand the higher level idea of why something is secure. So we start here with the definition of what a pseudorandom generator is. It's something that takes in a key, stretches it, and spits out something bigger. There's a little bit of description on the side. We've got some color coding for later. And how do you use a pseudorandom generator? Well, you take a message, you stretch your key to be the same size as the message, and then you XOR them together. That's how you encrypt a message using a key that's smaller than your message. That's the point of a pseudorandom generator. Lets you stretch your key. Hopefully, a pseudorandom generator is indistinguishable from an actual random generator. So, what does it mean for this encryption to be broken? How do we know that this is secure? What's the metric? So we have this attack game where the adversary sends over 2 messages. The challenger picks one of them at random, picks a random key, and encrypts that message, sending it over. The adversary then has to decide which of those messages was encrypted. If they do better than 50-50, that's an advantage, and the encryption is broken. Okay, so say that I have an adversary like this. I want to build an adversary B that has this as a subroutine that breaks the pseudo-random generator. That's my claim, that's what I want to do. So from the challenge, or from the environment, I get some randomness or pseudo-randomness. I don't know, I'm trying to guess. How I use this as my program is I take this in as my extended key, pretending it's pseudo-random for a moment. I get 2 messages from this black box. I choose one of them at random. I XOR. I give it back. It guesses which one. If it guesses correctly, that's evidence that it's pseudo-random, maybe, more likely than not. And if it guesses incorrectly, then it's more likely to be truly random as opposed to pseudo-random, the thing that I XOR'd in. And there's a little bit of analysis here with the actual probabilities on the side, but that's kind of the high-level idea. And with all of these boxes, the hope is that it kind of visualizes things in a way that forces you to literally black box things, as opposed to getting mired in all the details that you would get if you experienced this in a written version that's fully technical, and it helps you stay relatively rigorous without being formal. And the goal is to make this interactive where you can actually click, drag, create boxes, etc. in the future.
Cool.
This is an educational tool.
Nice. Awesome. Do you have anything on like some simpler cryptography, like just like Diffie-Hellman RSA, something for like learners who are just getting started with that?
I don't currently, but this took me about 30 seconds with Claude to point it at something and say, here's how you write things, build me this thing. And in the future, I also want to make it so that users can interactively build these things without going into the back end.
Cool.
Cool. Yes, but I would say that the RSA security proofs and stuff like that are much more complicated than this.
Really?
So I picked this for its simplicity.
Cool.
I'm sure that if I gave something like this to Jonas Nick, he would say, no background is required in order to understand what is in this write-up.
Cool.
I love Jonas Nick, of course. I'm mostly joking.
Well, thank you very much for your time with that. Yeah.
All right, so the problem that I'm trying to solve is people don't really understand why Bitcoin is secure. And when you throw out terms like cryptography, encryption, math, they freeze up. So the solution is a fun little game that kind of walks you through why Bitcoin and the internet and all of that crypto-based or cryptography-based stuff is actually secure. And it is modeled on RSA rather than ECC. That's just because making a game for ECC was kind of annoying. RSA is very easy to create a fun little game. So the way it works is like this. You can choose your difficulty level. We'll start off easy because at the basis, it is pretty easy. You are given a number and you have to figure out the 2 prime numbers that multiply to create it. In this case, we have 35. So a nice easy one, it's 5 and 7. Let's say we get it wrong, though. We try to crack it. Now, 5 times 8 is 40, not 35. So let's try again, and this time we crack it. And would you look at that? We got it correct. Your reward is, for the easiest level, 1 Satoshi. And you can also claim via wavelength. So while that loads, we can test it. 1 Satoshi, it's on the way, and we got it. And Signet works as well. Now, of course, as you increase the difficulty, it gets really hard. Good luck finding out the prime numbers for that one. And it gets worse. And this is getting too close to the level that it's actually based on. If you can figure this out right now, I will personally send you one Bitcoin. But if you can't, you can cheat. So let's cheat to figure out what it is. There we go. So it's 6 Satoshis. That's double the reward of solving it because it doesn't pay to cheat. And as you can see right away, bot, the 2 numbers generated. Let's double check that it's accurate. Access granted. Nice. And now you can claim 3 sats back. Or, right? Now it does integrate wavelength, lightning, super fun. It is, though, I believe on testnet since prod is currently invite only. And as well, when you hack Bitcoin, an open timestamp is also created. So it is on the blockchain right over here. It even says the number and the level that you had, of course, with the time, so the world knows. So as you go through it, you can see that at a really small level, it's easy. But the difficulty really comes from really big numbers, a million different possibilities.
Well, that's time. Thank you.
Thank you.
I guess what would it be? Just one quick question. What would be required to add ECC instead of RSA?
So there, the game is a bit more complex, a little bit less intuitive. One was kind of like how many jumps it would take to get to your answer. Because with CC, you keep doing like the tangent of the point. But there's a bit more. There's more rules you would have to understand in the game, and not as intuitive. With RSA, it's even a third grader can do it.
Can understand the rules very easily, and then know the number.
Yeah, and understand where the difference is.
Yeah.
Perfect. Thank you so much. Yeah.
All right. So to start, this was built 100% with Soapbox, Shakespeare. This is my first hackathon, so I'm a beginner. It's 100% void coded. So, the problem I'm trying to solve is finding signal in the device in the BIP 110 debate. So a lot of people are looking at signaling data, but I don't think that's necessarily the right data to be looking at. I want to see, I believe, a leading indicator of whether a mining pool is going to flip is going to be compliant blocks that are not signaling. Because it's very easy to flip a bit when it's more difficult to change the way you construct blocks, so you're going to do that ahead. And so I found some data by Kilombino, who has a fourth mempool, that tells you which blocks are dirty in his opinion. I'm kind of neutral here. Which blocks are compliant but not signaling, and which ones are compliant and signaling. And I extracted that data, and I want to see it on a pool-by-pool basis. And as you can see, there's like a roughly 60% ambient level of compliant blocks. That would be this column here, that are not, well, most of them are not signaling. Like all of them are not signaling except for Ocean. But that ambient level is just, I think, due to randomness. That's just like how the blocks come out. But if my leading indicator is true, then in the days and weeks before the activation date, you'll see this number flip to 100% on whatever pools are going to be flipping the bit. And as you can see, Ocean has a much higher compliant rate and a higher signaling rate, which is roughly equal to the difference between the percentages. So it's kind of what you would expect to see. So right now it's not particularly interesting data, but you can also see trends. So I'd be monitoring this going up to the
question. With regard to the signaling, I know that some miners tend to use random numbers for version. Do you have an idea of what the old numbers used to be to check the difference? Because I'm guessing that there must be some sort of signaling that it's just related to random numbers in the version bits and not because true signaling.
To be honest, I don't know. I would imagine like
right now, just that bit is being kind of designated informally as the signaling bit. So I'm not sure if it's that.
No, because in the past, many people use whatever, and they only pay attention to that when there's time to support. So that there may be similarities in the past, and it doesn't show real support. It would be interesting to show the comparison with the past.
Okay. Do you know like compliance? As if like, no, you said like compliance.
With BIP 110.
Yeah.
With BIP 110.
Yeah.
So are there mining tools or mining laws on some? Do you think that's out of? Do you think it's just that there's no NFTs?
Yeah. Yeah, because those are centralized pools. So if they're going, you would expect to see either the ambient levels of random blocks that happen to not have any non-compliant stuff in them, or 100%. Like it's kind of either or. Whereas with Ocean, it's a little different because they let the miners build their own block templates and signal on their own, which is why you see a 20% difference.
Thank you.
Thank you.
So, today we are at the BTC++ Toronto Hackathon, and I presented an integration of the block compact filters that was presented by the BDK team earlier today. So why do we want to implement that in Bull Bitcoin wallet? It's because we care about privacy, and obviously, as of today, the user rely on some default Electrum servers that we put in the wallet, but they also can set up their own Electrum servers. Some people don't do that, and some people use Tor to mitigate the risks. But Tor doesn't solve all the risks because your IP is likely to change each 10 minutes. So when you do some sync request, you may leak some information about your wallet, basically your addresses. And with this solution of compact block filters, you could sync your wallet without having to fear to reveal this information. So that's why it's really important to us to have this kind of alternatives, I would say, to sync wallets.
One thing that I would say just establish, so before you did not have BDK as part of Bull Wallet, and now you do.
No, we always used BDK since the beginning. It's just that at some point we were using BDK Flutter that was developed by another team that was using Flutter Rust Bridge for the bindings. And as they presented during the conference, the BDK team switched to Unify, which is a project maintained by Mozilla. And we use now their version of BDK through Unify. So this is the last switch that we did that is way more updated than the BDK Flutter that we were using before.
Okay, and then I want you to tell me about Bull Bitcoin's wallets as a privacy wallet. Like, why is it a priority that privacy features go into the wallet, and why is compact block filter part of that?
So to me, as a contributor of the wallet, I think privacy, I mean, we are in the consensus conference, right? But I think among the value of Bitcoin, privacy is one of the most important consensual value. And basically we may have some, activists that use the wallet, and we don't want to risk their privacy because it can totally break their life. So we may protect the user's privacy at all costs. That's it. We don't know how it can involve in their life. The risk of using a wallet shouldn't
be risky, basically.
And then, so you presented at the hackathon. How far along were you in development? So how much is done?
Okay.
And what are we waiting for to come live in the real wallet?
So the deadline was quite short, so it's mostly vibe coding right now. But this first integration is basically you start the wallet, you arrived on the wizard. On the wizard, we have this new page that offer you the possibility to turn on the block compact filters. If you turn on this option, after importing your wallet, you will start the synchronization that may be long because you have to synchronize all the block filters headers, and then you have to download all the block filters. So as of now, we sync from the whole time. Since the block genesis, we should not. Of course, the next iteration should be we sync from the wallet birthday, so it go way faster. And we have to improve the UX, of course. We have to deal with background tasks and find a way to improve all this user experience and make it usable.
Thank you.
Thank you.
And now, our conduition is going to talk about some quantum fun, right? Using memes. So, please, welcome conduition.
Thank you. Hey, everyone. Thanks for coming today. Today, you're going to learn about isogenies in 30 memes or less. So let's get started. Many companies are now promising us scalable quantum computers in the next few years, and NIST has meanwhile mandated that classical crypto be sunsetted by 2035. And well, these timelines have Bitcoiners kind of worried and seeking paths to quantum security, and any such path will necessarily include post-quantum cryptography, and that leads us to isogenies. Isogenies are an emerging branch of post-quantum crypto that stand out for their very compact keys and compact ciphertexts and compact signatures, and because they have a very surprising degree of mathematical flexibility that lets us do all kinds of fun things like BIP32 quite easily. It's very fashionable these days to opine on the status of quantum computing and its feasibility or its lack thereof, but personally, I'm not going to touch that today. I think it's actually impossible to accurately predict when Q-Day will happen. And so instead, today, you and I are going to focus on a particular mathematical tool that we may be able to use if and when quantum computers do turn out to be a significant threat to Bitcoin. Some disclaimers before we start. I am not an isogenists. I am not a mathematician. There are some in the room today. I am a cryptographic security engineer. And that means while I can build cryptographic code and audit it, and maybe I can find bugs, I'm maybe not the best authority on the mathematical lore behind these crypto systems. But that's exactly what I'm up here presenting about today, so you should take what I say with a grain of salt. Because everything that I learned and that I'm about to tell you, I learned only in the past year, and I only learned about it by reading the works of much smarter people than myself. So treat this talk only as a springboard to deeper learning. I cite all my sources at the end, and I encourage any curious readers to go and pursue them. Second disclaimer, this talk is going to contain a lot of math. Sorry, that's not really avoidable. But in order to ease digestion, I've tried to present at least half the information in the form of memes. So I'd like a show of hands now. Who in the audience would say that you have a comfortable working knowledge of classical elliptic curve cryptography, of the kind that we use in Bitcoin today? Okay, wonderful. I have great news for all of you, which is that much of what you already know about classical elliptic curves can be reused in the context of isogenies. And this is because although the assumptions and the rules are very different, we use many of the same objects, the same mathematical concepts and terminology in both isogenies and classical elliptic curves. Let's get into some technicals. First, what even is an isogeny? Well, if you look it up online, you'll probably find a formal definition like this, a surjective morphism between a billion varieties with finite kernel. But I want you to think of an isogeny more informally today as a function that maps points on a single elliptic curve to points on a different elliptic curve while preserving the two curves' structures. And we typically write them like this. This is a statement that says phi, that's the letter on the left there. Phi is an isogeny from the elliptic curve E1 to the elliptic curve E2. We call the curve E1 the domain, or the input curve, and the curve E2 the codomain, or the output curve. And when we evaluate an isogeny, we write it like any function, passing in an input point in the domain, and we get an output point on the codomain. Isogenies, since they're functions, can be composed as long as their domains and codomains align correctly. Here we can denote composition with a little circle operator. And in this case, our example between phi1 and phi2 only works because the domain of phi2 is the same as the codomain of phi1. Otherwise, you cannot compose them. If you do, you get an isogeny from E1 straight to E3, going through E2, by the way. Isogenies share a lot in common with polynomials, including the concept of degree. Every isogeny has a degree, and much like in the context of polynomials, the degree of an isogeny is a measure of the amount of complexity contained in the isogeny. And just like polynomials, when you compose isogenies, you multiply their degrees. Every isogeny has something called a dual, which you can think of as kind of inverse. It's not quite the same, though, because composing an isogeny with its dual actually multiplies the input point by the degree of the isogeny for technical reasons we will not get into today. However, the upshot is that if you're given an isogeny, say from E1 to E2, it's very easy to find the dual isogeny that goes from E2 to E1. This will be very important for security later, so please remember this. I should also talk about isomorphisms. An isomorphism is kind of like a degree 1 isogeny. It's a little more complicated than that, but that's how you should think of it for today. And if there exists an isomorphism between two elliptic curves, then we say those two curves are isomorphic. And we write that condition with this little congruent symbol right there. It's very easy if you're given two elliptic curves to tell if they're isomorphic. And if they are, it's very easy to find isomorphisms between them. In this way, the two curves that are isomorphic are kind of fungible in a way. Now, in classical elliptic curve cryptography, we kind of think of elliptic curves as like a fixed parameter of our crypto system. We just pick one curve, like SecP256K1 or ED25519, and we just kind of use that curve again and again. But for isogeny cryptography, we kind of have to become a player, because isogenies are basically cucks. Their defining purpose is to see their domain and codomain curves connect. And these isogenies will later become our secret keys, and the curves that they connect will be our public keys. But we cannot just use any elliptic curves. Not any will do. We must specifically focus on supersingular curves. This is a subset of all elliptic curves. And if you look up what supersingularity means in this context, you're probably going to find this Wikipedia article with this vast array of different equivalent definitions. But I think the simplest one, at least for me to parse, is this one. Let me break this down for a second. The number p is a large prime, typically 256 bits or large. And fp to the k is the finite field containing p to the power of k elements. Sorry, I'm not going to get into what finite fields are today. But this whole expression, if this evaluates to true, oh, sorry, by the way, the notation on the left is a way of saying the number of points on the elliptic curve E that are in the finite field fp to the power k. But if this whole condition is true, and you can test for this, then you say the curve is supersingular. And then, from that, you get a whole bunch of other properties about that curve automatically. So why are we so interested in these specific supersingular curves? Well, there's a lot of reasons, and the main one is actually quantum security. If you use curves that are not supersingular for cryptography, they become vulnerable to quantum attack. And to understand why a little more, let's look at some facts, and we'll see where they lead us. Just stay with me for a minute here. First of all, fact number one, every supersingular elliptic curve is isomorphic to a supersingular curve that is defined over the finite field fp squared. Remember what we talked about a minute ago about isomorphisms? How any two curves can be isomorphic, and if they are, you can easily map points between them with isomorphisms that you can deduce. Well, that means if you partition the set of all supersingular curves into buckets called isomorphism classes, every curve falls into exactly one of these buckets. And curves in the same bucket are kind of fungible because you can kind of easily map between them. And if you look at each of these buckets, rule number 1 here says you can pluck at least one representative curve from that bucket that is defined in this finite field fp squared. Why is that important to us? Well, for cryptography, we tend to want to compute stuff, and not every curve in that bucket is going to be easy to compute with. Some of them might be defined over the finite field fp to the 4th, or fp to the 8th, or even bigger. And those are very awkward to work with. So we like to work with curves that have efficient arithmetic, and fp squared gives us exactly that. Fact number 2, every supersingular curve defined over fp squared is connected to every other such curve by an isogeny that's also defined over fp squared. This is just a way of saying that each of those representatives we were talking about a second ago, those are all connected by isogenies that are efficient to compute. And fact number 3, any isogeny of degree d can be factored into a chain of isogenies with prime degrees that correspond to the factors of d. So essentially, this is a way of breaking down any isogeny into its prime components in a kind of way. Now, if you take facts 2 and 3 together, you can construct this, the supersingular isogeny graph, where the vertices of this graph are those buckets, the isomorphism classes that we talked about a second ago. The edges that connect them, those are all prime degree isogenies. Walking from one vertex on this graph to any other is equivalent to finding a chain of prime degree isogenies that you compose together one after another, kind of like hopping from one bucket to another. And the cryptographic properties of isogeny cryptography come from analyzing the properties of these supersingular isogeny graphs, among many other things, particularly for very large primes p. Now, I want to delineate between the prime p, which we call the characteristic of the finite field, and the prime degrees of the isogenies in these graphs. They're two different concepts. But if you make the prime p, the characteristic, bigger, you get a graph with p over 12 vertices, p over 12 buckets. That's a pretty big number. If p is like 2 to the power of 256, that's 2 to the power of 256 over 12. That's still a very huge number. Now, this is where we get to introduce the core hard problem of isogeny cryptography. If you make this graph really big, its structure becomes incredibly chaotic, and it's very hard to know where you're going as you walk through it. So the problem that we use is called the supersingular isogeny path problem. And it asks you, if you're given 2 supersingular elliptic curves, can you find an isogeny between them? Seems like it should be easy because there's many different paths that one could take through that graph. And actually, since there are many prime numbers, there are many different graphs that you could walk through. But finding even a single path seems to be very hard. You can walk through the graph and search to try to find your destination, but it's hard to know how far you are from it. And it seems like the only viable general algorithms for this have complexity that's about the square root of p. So for a number 2 to the 256 value of p, then you'd have about 2 to the power of 128 work needed to solve this problem using, say, meet in the middle, which is the best known general algorithm. And quantum complexity is, of course, a little bit better because of the speedups that you get, but you only still have at best the 4th root of p efficiency. Okay, let's take a little break and switch gears here for a second, because so far we've been talking only about isogenies between different elliptic curves. There are also isogenies within elliptic curves, and we call these endomorphisms. These are functions that map points on a specific curve to different points on the same curve, but still preserving the curve's structure like any isogeny should. Can anybody give me an example of an endomorphism? I'll give you a hint. Everyone in this room uses them constantly. Tadge? Yes. Point multiplication. Thank you. That is an endomorphism because it is a structure-preserving map that returns points on the curve to different points on the same curve. There are also others. There are, say, for example, the Frobenius map and composed isogenies. And ultimately, though, there are only a finite number of these endomorphisms on any given elliptic curve. If it's defined over a finite field, there are only so many different operations you can do, right? And this gives a finite set And if you compose and add these endomorphisms together as functions, as you can with the functions that have the same domain and codomain, you can compose what's called an endomorphism ring. This is a closed mathematical group, kind of like a polynomial ring, if you've ever heard of those, but with endomorphisms as the units in this particular ring. Computing a generator of this ring is a hard problem in the case of supersingular curves, and we call this the endomorphism ring problem. This is hard even for quantum computers. And in the 1940s, a mathematician named Dryja proved a very neat theorem. He showed that every supersingular elliptic curve has an endomorphism ring that can be very neatly expressed in the language of quaternion algebras. Here is where I'm going to start glossing over some math here, because to tell you the truth, I don't understand this part of the field nearly as well as I should, and since I'm not confident in what I do know, I don't want to mislead you. Instead, I'm going to skip straight to the upshot of Dryja's correspondence, which is that the endomorphism ring problem and the supersingular isogeny path problem, those are equivalent, unconditionally. If you can solve one, you can solve the other. Namely, let's look at exactly what you can do. Say you're given two supersingular curves, E1 and E2, or sorry, E0 and E1. Let's assume that we already know the endomorphism ring of E0. If you are given the endomorphism ring of E1, let's say if you had some magic algorithm to break ERP, well then you could find an isogeny from E0 to E1 quite easily by doing some quaternion math. And conversely, if you are given an isogeny from E0 to E1, say if you had a magic algorithm that broke SIP, well, then you could find the endomorphism ring of E1 quite easily. Again, using quaternion math. And that's exactly what some algorithms can do. This is all computable using such an algorithm as KLPT. Now, the brains of the cryptographers in the room should really be lighting up right now, because I've just told you that we have two hard problems, quantum hard, that are apparently equivalent, and which we can solve if we have a special piece of information, like an endomorphism ring or an isogeny. Let's see how we can use this framework to build a simple toy signature scheme. We will start with a base elliptic curve, E0, and we assume its endomorphism ring is publicly known. There are curves like this, by the way. And then we generate a random isogeny, phi, that goes from E0 to some other supersingular curve that we'll call suggestively EPK. And then we compute its endomorphism ring using some Dryja correspondence math. Well, now we can publish EPK as our public key. More particularly, we publish the elliptic curve equation of EPK. And this is actually very compact, especially if we use Montgomery curves. Because here, we only need to publish a single coefficient, A, which is just one finite field element. Very succinct. The endomorphism ring, we keep as our secret key. This is not as compact, but that's not such a big deal, because we typically don't need to send our secret key over the wire. And if we do, we can use the isogeny representation with phi, because that actually does have a compact form, which we'll get to later. Now, let's see how signing works. Oh, I should maybe back up for a second. You might be wondering why it's possible to just generate a random isogeny like this, given I just told you that finding isogenies is hard. But actually, this is a different problem. Finding an isogeny that starts at E0 and goes to any curve is relatively easy. This would be equivalent to taking a random walk on the isogeny graph and just randomly hopping from bucket to bucket a certain number of steps, and you just stop after a certain point. It's much harder to find an isogeny between two specific curves. In other words, if you're given just a source, you can find an isogeny very easily. But if you're given a source and a destination, that's hard. OK, let's look at signing. So remember, we have our base curve E0 and our public key curve EPK. And we have one isogeny between them. And we know the endomorphism ring of EPK. We'll now derive a challenge isogeny by hashing our public key with a message. And we'll call this phi challenge. And we'll call its codomain E challenge. And then we will compute its endomorphism ring. We can do this because we know our secret key, the endomorphism ring of EPK. And we know phi challenge. So as I said earlier, if we can break SIP, we can break ERP, vice versa. We can do the quaternion math and figure out the endomorphism ring of E challenge. And then we use this endomorphism ring along with the public constant endomorphism ring of E0 to find a new response isogeny from E0 straight to E-challenge. And now we can publish this response isogeny as our signature. This proves we knew our endomorphism ring because we couldn't have computed this without it. We couldn't have computed the endomorphism ring of E-challenge, so we couldn't have found phi resp. But there's a big problem with this. Can anyone see it? Remember how I told you earlier that every isogeny has a dual and it would be important for security later? That pays off now because phi challenge has a dual. I just revealed an isogeny from E0 to E-challenge. If you compose phi challenge's dual with phi resp, you get an isogeny from E0 to EPK. That reveals our secret key. So yes, on one hand, we did prove that we actually know our secret key, but we only did so by revealing it, which is not so great. In cryptographic terms, this scheme is sound, but it's not zero knowledge. In order to get zero knowledge, we need to add a 0th step, where we sample a random commitment isogeny that we'll call phi com, and we compute its endomorphism ring. We keep phi com and its endomorphism ring of ecom secret, but we include phi com in the challenge hash when we're deriving phi challenge. And then, when we're finding our response isogeny, we do so from ecom to E-challenge instead of from E0. This is important because we keep phi com secret, and this prevents any observers looking at our signature from finding an isogeny path from E0 to EPK. In a way, this is kind of like the nonce in a Schnorr signature. It protects our secret key with some randomness that the attacker can't predict. But like Schnorr signatures, there are caveats here where you can't reuse a commitment. And if you do, it leaks your secret key. This is because if you reuse the same commitment in 2 different signatures, it reveals something called a non-trivial endomorphism, which lets anyone recompute your entire endomorphism ring. Sounds pretty cool, right? So we've actually finished this now. This is a relatively secure signature scheme. Of course, I've glossed over all of the quaternion math, but still more or less accurate. Cool, right? But, well, actually, you guys just learned how SkiSign works. I just described the NIST PQC Round 3 finalist SkiSign to you. Although I've omitted a lot of details and glossed over quite a bit, this is more or less how it works. Now, to review, a SkiSign public key is just an elliptic curve, specifically a Montgomery curve. And a SkiSign signature is just a commitment curve and a response isogeny from the commitment curve to some pseudo-randomly derived challenge curve. The verifier will recompute the same challenge curve, the same challenge isogeny, and find the same challenge curve. Then they'll just check that phi response is a valid isogeny from ecom to E-challenge. If that is true, then that is sufficient to prove knowledge of the endomorphism ring of EPK. Now, I have explained why public keys are so small, because it's just a single Montgomery curve coefficient. However, I have not explained why the response isogeny is so small. And this is because, well, remember when I told you earlier that SkiSign signatures are only 148 bytes or so? Well, 64 bytes are taken just with ecom, because that's how much you need to encode a elliptic curve when its coefficient is encoded as a finite field element in fp squared. That leaves only 84 bytes left for our response isogeny. So how do they get it so small? The answer has to do with kernels. Every isogeny has something called a kernel, and it can be represented uniquely by its kernel. Well, almost uniquely, but it can be recovered more or less completely from the kernel. And so if we can find a way to encode the kernel, we can find a way to recover an isogeny. Now, the kernel is the set of all points that the isogeny annihilates. More specifically, if we have an isogeny from E1 to E2, the kernel of that isogeny is the set of all points in the domain curve, say E1 here, that phi maps to infinity on the codomain curve. Remember that every elliptic curve has this distinguished point called infinity, which you can think of kind of like 0. It's the identity point. The Infinity point on the domain curve is always part of the kernel in any isogeny. That's just an invariant of the isogeny. But the rest of them are just elliptic curve points, right? So if we could encode those, we could encode the entire isogeny. But there's a problem with this, and maybe you can see it from my notation here, which is that the number of points in the kernel scales with the degree of the isogeny, which is typically very, very large, like 2 to the 128 or more. So obviously encoding 2 to the 128 points is not very conducive to a compact signature scheme. However, there are ways we can represent large groups of points pretty succinctly. So now, in order to do that, we need to talk about torsion groups for a second. The t-torsion group of an elliptic curve is the set of all points where multiplication by t annihilates that point. In other words, t times p is infinity. Now, a more intuitive way to think about this is if you pick a point p in the t-torsion group and you just add it to itself again and again and again, you get p and 2p and 3p and so on until eventually you get to infinity after t additions. Now the interesting part. If you pick a point in the t-torsion group, that point is a generator of a so-called cyclic torsion subgroup of order n that divides t. By cyclic, I mean if you take p and add it to itself again and again, it eventually, after generating n distinct points, it wraps around and goes to infinity, and then p, and then 2p, and so on. So in a way, addition is kind of cyclic. Now, there's an important distinction here between what a point of order n is, like this one is here, and a n torsion point, or in this case, a t torsion point up here. And this tripped me up when I was first learning about this, because a point that has order n is part of the n torsion, but a point that is a member of the t torsion group does not necessarily have order t. It might have some order that divides t. That's because, let's say we have a point p with order n, where where p plus p plus p plus p over and over again generates n distinct points. Multiplication by n maps p to infinity, so 0. Now, that means that p is also a member of the n torsion, and also the 2n torsion, and the 3n torsion, and so on. So anyway, the point is that a p may have one order, but many different torsion groups it might be a part of. Okay, take a breath. That was a lot of math. Let's digest that for a minute and remember why we're doing this. We're trying to find a way to encode our response isogeny succinctly. We can do that if we can represent its kernel, and we just found a way that we can represent a kernel. Because remember, that single point p generates a whole bunch of points. Like it might be 2 to the power of 256. It might be a huge amount. And so if we can find a way to ensure that the kernel of our isogeny is generated by a single point, then we can represent that entire isogeny with just that one point. There's just one problem. Not every isogeny has this property. And we call an isogeny that does cyclic, because it has a kernel that is a cyclic torsion subgroup. Now, the good news, though, is that we can decompose any isogeny into one that is cyclic, that has the same domain and the same codomain. This only works in certain scenarios, though. Namely, it only works for isogenies that have so-called smooth degree. However, the upshot is there are isogenies we can represent by just a single curve point, which is pretty succinct, usually just like 64 bytes or so. If we want to be able to encode any arbitrary isogeny, then we need to start talking about things like Kani's lemma and higher dimensional isogenies, which we're not going to do today because I don't have the time. You can also optimize this encoding a little more, because the point p can actually be encoded and compressed a little more using something called torsion basis points. But again, there's a lot below the waterline here that I'm going to skip over here. And this is really the beauty of elliptic curves, because they have just such rich depth of structure that even though we might want to get rid of them after Q day, the irony is we might just come crawling back to them because of their rich feature set. And now, with the only few minutes that I have left here, I want to talk about key re-randomization. This is a subject that should be near and dear to every Bitcoiner's heart, because although you may not know it, you use this every time you use your wallet. The key thing that we want from key re-randomization is the ability to take a public key and, with a salt, scramble it into a different public key that looks unrelated to the first, but in such a way that the original owner of that first key can reconstruct a secret key to the new one that we scrambled. This is incredibly useful and allows us to do many things like BIP32 public key derivation, taproot key tweaking, silent payments, and probably quite a few things that I haven't even thought about. And this is very easy with elliptic curves in a classical context. I've shown here a little way of how to do this with classical elliptic curve discrete log crypto. I won't really go over it too much because I think it's very well documented. The only difference between these other Bitcoin-based schemes and the one that I'm showing here is what we use for the salt. Otherwise, it's the same. The salt in Taproot is the root of a Merkle tree of scripts. The salt in silent payments is an elliptic curve Diffie-Hellman shared secret. The salt in BIP32 is a chain code and an index. It's all the same primitive, though. It's re-randomization instantiated in different ways. So it would be really cool if we could do this in a post-quantum context, but it's just not looking that good. Because hash-based signatures, well, this is kind of impossible. There is no algebraic structure to be had at all in hash-based signatures. Lattice-based signatures are looking a little better, and the state of the art is advancing every few months. But ultimately, we always seem to need to make trade-offs. We need to change the signing algorithms and the verification algorithms. We need to change the key formats. We need to change the signature formats. We need to change the sizes of the signatures in many cases. The best one that I know of is called dilithium RKC, linked here. And it provides us with a re-randomization scheme on top of dilithium, which changes the format slightly. So you have slightly larger keys and signatures. I think it's like 20% larger than stock dilithium. But you also get 2 to 3 times slower performance. However, isogenies really take the cake here because we get drop-in key re-randomization with almost no changes. Actually, with no changes at all to the default signing and verification schemes, the key formats. They're all exactly as they exist in the literature today. All you need is an algorithm to do key re-randomization, which I'm going to show you now. Here's how you do key randomization with isogenies. You start with an elliptic curve public key, EPK, super singular, of course, as always. And then you derive a pseudo-random isogeny that starts from EPK and goes to some arbitrary random other elliptic curve that we'll call EPK prime. You derive this, as usual with re-randomization, by hashing the public key in a salt. And then we just return EPK prime as the new public key. This is very fast and easy to compute. It requires no quaternion math. It's also very simple to implement. Contrastingly, the re-randomized secret algorithm is a little more involved. You're given the endomorphism ring of EPK because that's your secret key, so you have access to it. And you derive the same pseudo-random isogeny, phi, and then you must find and return the endomorphism ring of the codomain EPK prime. This is a little more complicated because you need to use the Doring correspondence and quaternion math, but still ultimately very doable. Also notice that this is actually the opposite performance asymmetry that we have in classical cryptography, where re-randomizing the public key is hard, but re-randomizing the secret key is easy. In the elliptic curve context, re-randomizing the public key is as simple as doing it's hard because you have to do an elliptic curve point multiplication, whereas re-randomizing the secret key would be easy because you're just doing integer addition. This way, it's the other way around in isogenies, because you need to do more work to re-randomize the secret key than the public key. Also, this has recently been proven secure, just like in June, so pretty cool. Okay, I'm going to start wrapping up now. Let's go over what we learned today. Isogenies are just structure-preserving maps between elliptic curves. And we've learned that they form a connected graph where the vertices are these buckets called isomorphism classes, and you can hop between them. These individual curves from these buckets, specifically representatives in FP squared, these are used as our public keys in isogeny-based crypto systems. The signatures in such a system are just a proof that we know a specific endomorphism ring of a specific elliptic curve. And they're represented on the wire as they're represented on the wire as elliptic curve points, which we can use to recover the isogeny. We've also learned these signatures are compact precisely because they have compact encodings, like those points, and that the security of these signature schemes relies on the hardness of pathfinding in the isogeny graph, and equivalently, the endomorphism ring problem. The public keys in these systems, we've also learned, can be re-randomized by using random walks, well, pseudo-random walks on the isogeny graph. There's a lot that I glossed over, though. As I've said many times, I've left out the entire quaternion math side of this field, which is rich and full of many opportunities. I've also elided any description of performance here, which is the main drawback of isogeny-based signature schemes. TLDR is they're pretty slow. Ski sign signatures take on the order of around a millisecond to verify, which would be not great if we just plugged it straight into Bitcoin. I've also not discussed how Connie's lemma and higher dimensional isogeny representations work. And if you're interested in learning more about the state of the art, this is absolutely required reading, because it is how every modern isogeny signature system expresses isogenies. I've also not talked about Prism, which is a newer, more cutting-edge signature system that is a little less tightly secure because it adds new assumptions on top of the ones used by SkiSign. However, it may admit some very interesting constructions, and it is easier to implement than SkiSign. Speaking of which, I've also not talked about the additional security assumptions added on top of SkiSign and Prism by those schemes in their security proofs. Short version here is that Prism and or SkiSign could be broken, in theory, without breaking the underlying assumptions like SIP and ERP. And this is mostly a question of whether certain special degree isogenies leak information about the endomorphism ring of your public key, and this is still unknown. Here are all my sources. I highly recommend you take a look. I'll be putting the slides up online on the BTCPP website afterwards for you to reference, but lacking that, why don't we shift into questions?
So, any question from the audience? You needed more memes.
Nah.
So, thank you very much.
Thank you.
All right. Yeah, so I'm curious, how many of you were at the Hoover Dam conference? No one? All right, so I have one person to apologize to, because this is exactly the same as the Hoover Dam conference talk. But, you know, I mean, you got to get practice, like getting better at presenting your ideas. And in fairness, you know, I have been busy trying to win a war. I've also been busy trying to win another war. But anyway, you know, tail mission and demirage. So let's start with a background to why we're talking about this at all, which is what is the role of proof-of-work mining? And I'll be honest, way back in the day when I was trying to be Satoshi and inventing Bitcoin, I completely screwed this up. You know, I always thought about proof-of-work as a really important part, as the thing that makes new coins. You know, you make the coins with proof of work, and I know the consensus thing somehow happens. Adam Back and I, back in the day, we did not get this. But the point is, it's not about making new coins. It's about consensus and about making sure that the network moves forward. Now, as a byproduct, we can make new coins, but that's not the primary purpose of it. So the other bit of background I want to talk about is, I think it's relatively clear that without a block reward, Bitcoin is definitely, from a game theory point of view, unstable. And what this really comes down to is, if miners are only incentivized to mine transactions, or mine blocks for fees, there are circumstances where it does not make sense to simply mine the next block. It makes sense to reorganize blocks. And the nasty thing about this is that incentive is relative to how much hash power you have, because your ability to reorg blocks goes up as your percentage of hash power in the total network goes up. And that, if that becomes profitable, that really screws us over. We don't see this right now because miners earn a ton of money just to mine a block to begin with, and then transaction fees are negligible compared to it. But I think the academia here is pretty clear that there is a potential issue. And you see this in how insignificant block fees have been. This is BTC and USD, and if you compare them to subsidy, well, subsidy dominates. So that's the circumstance we're in right now. Everything you know about Bitcoin empirically, as in how well Bitcoin works, well, that's the data you're going off of. If you think Bitcoin works well, that's the environment. And as things change, we're getting into environments that we've never dealt with, and indeed no real decentralized currency has. And while yes, there have been things that have driven Bitcoin fees in the past, like inscriptions and so on, these things seem to be kind of a flash in the pan. There's inscriptions a little after that screenshot was taken. And notably, going from putting JPEGs into the chain to putting some things much smaller into chain, the inscription community changed in a way where Rally didn't really drive that much fees again. So, what is tail emission? Well, if you just have a fixed reward per block, the curious thing about it is it actually converges to a stable monetary supply. That is, the reward converges to the rate of lost coins. And my political argument is, had Satoshi back in 2009 released Bitcoin, and it was like, say, 1 Bitcoin per block, we all would be talking about Austrian economics and how Bitcoin is this, digital gold-like thing where, there's a fixed supply and so on. The politics of this are actually exactly the same. And probably people would have noticed this and said, oh, yeah, it's very clever. Yeah, it has this fixed supply, but this clever bit. But for most part, everyone would just say, yeah, obviously it's gold-like. In the same ways right now, we say, well, yeah, it's just gold-like. Now, you can actually do this mathematically and convince yourself with a bit of differential equation stuff. But, I went to art school. I'm not that far down the street there. And then later on, I did part of a physics degree before dropping out and doing Bitcoin stuff because physics is hard. So I don't know, that looks kind of hard. Yeah, there's more hard stuff there. We could do an analogy instead, which I think is much easier to understand. Although when I did it at the Hoover Dam, I tried to be clever and do it with a Hoover Dam physical model. Unfortunately, in Toronto, the only relevant one is we have the sewage interceptor pipe. It's a couple kilometers long. It collects all the sewage, and yeah, let's just go back to the bucket and spigot. All right. So, if you have a bucket, the rate at which water comes out of a hole at the bottom of the bucket is dependent on the pressure in the bucket. And the pressure in the bucket is dependent on how much water is in it. All right? More water pushes more water out the hole. So if you add a fixed amount of water per second to that bucket, if the water level is below equilibrium, it'll gradually rise. More and more pressure flows out till the pressure flowing out of the bucket matches the amount of water coming in. If the amount of water in the bucket is higher than equilibrium, well, that pressure will force more water out. More water will come out than is being added in, and it will get back to equilibrium. Now, in a real bucket, there's supersonic flow and all, but as an analogy, this works great. Now, why does this work for Bitcoin? Well, in a tail emission scenario, you have a fixed amount of coins getting created per unit time, right? Some amount of coins per block, and you have a rate of loss, which is how many Bitcoins get lost by people. Now ask yourself, is that rate of loss dependent on a number of Bitcoins or dependent on a percentage? Do you care that you have 1 Bitcoin or 10 Bitcoin when it comes to how likely you are to get into a boating accident? The number doesn't matter. It's a probability. Now, certainly, if you don't care about Bitcoin that much, yeah, you might be a bit more, a bit less careful with your coins. But when you compare different people, there's no scale effect here. I'm worth whatever amount, you're worth whatever amount. You're going to care about the percentage of your wealth in the same way. It's not the number that matters, it's the probability of failure. And yes, these probabilities will go up and go down, but we know that eventually these things will converge. Now, a real world guess for how likely it is for people to lose Bitcoin every year, it's probably in the range of like 0.1% or something. So if you set a tail emission that roughly looks like that, it will converge. But yeah, and like I say, it's a myth that you need to know. It will converge. But implementation is an interesting thing here. Now, Monero has tail emission. Why did Monero add tail emission? Well, Monero added tail emission because Monero decided to do a block size that was variable. And the way that the block size is variable in Monero is miners sacrifice something to get bigger blocks. And the idea is, well, if they really want bigger blocks because of high fees, they can sacrifice their subsidy and it will all kind of balance out and so on. Now, I'm not here to argue Monero is doing a good thing with that. There's certainly scenarios in there where repeated fee demand eventually makes Monero fail from a consensus point of view. But because they needed this in their design, they needed Monero to always be created. And what did the Monero community do to add this? Well, they did a hard fork. Put up your hand if you think it's likely we're going to do a hard fork in the next 5 years for any reason. I like this guy. Yeah, I mean, all right, even if we could agree on tail emission, you're not going to do a hard fork for this. But, we can talk about that in a second. But then the second issue I want to go talk about is the economic side of this. Now, again, we went back to, we want to potentially do this to ensure that there's always a reason to push the blocks forward. So, does this really make sense? Are we going to have enough tail-limited coins to always give an incentive to push things forward? Well, the simple answer there is it's not clear. And why is it not clear? Well, because fundamentally these things are kind of unknowable. I mean, what is fee demand relative to other things and so on? But you can go make an argument from a different direction, which is clearly having some kind of level of subsidy, some kind of incentive to always push the chain forward is better than not having it. Right? You're always going to be in a better position from a security point of view and incentives to screw with the chain basically point of view, incentives to reorg point of view, if there's some reason to do that. So you can clearly say a tail emission from that perspective is better. But like everything, I can't guarantee things. And yeah, can Bitcoin add tail emission? Well, I think the answer here is probably not likely, but there's another way to do this. And I want to ask you guys, do you think inflation is a tax? Let's see how many Austrian economists are here. Come on, put up your hand. And is inflation a tax? I'm liking this. Well, what type of tax is inflation? One way to put it is to say inflation is a tax on your savings. That is, if you have something that is being inflated, in 1 year, the inflationary rate has effectively taken part of what your ownership is and rediluted it to whoever got the benefit in inflation. It's a tax. Now, yes, the fiat governments of the world aren't going to go say that, but I think economically, we can easily agree it's a tax. So, could you implement tail emission in a different way by just taxing coins? And the answer is yes. Now, demurrage as a concept refers to the idea of having a currency where over time the amount of it you have gets reduced. And I'm not claiming that my use of the term demurrage is strictly correct here, but the concept is if we have a tax directly on holding a coin, then we can use that money for the same purpose that tail emission would be. How do we implement this? Well, you can do this in a backwards compatible soft fork. You can look at it with a bit of math. And all I'm really saying here is if you have the value of every TX out spent in a block, sum that up, and then apply some rate, you can say that should be the total, or sorry, sum that up, multiply it by the time the block, the transaction has been in existence, that in units wise is coin days spent, all right? And if you multiply that by some rate, you can say when a block is created, that should be the total tax collected. And what you can do with this is you can create a consensus rule, a very narrow consensus rule that sums up that number D and says there must exist a transaction output in the block, or sorry, in the Coinbase transaction that takes all that money and assigns it to an output that effectively can be used as a fund for miners. Now, we don't need to get into the exact details of exactly how you go do this. There's a lot of different ways, but the important thing is you take this tax collected, you stick it into a fund, and then you allow miners to then take some of that money out. Now, an obvious way to do that would be to say, well, at any moment, miners can spend up to a certain percentage of that fund, and if that percentage is low, that will spread out this tax over a long period of time. And everything I said here is a soft fork, right? We've added a new rule that says blocks must have this certain structure in their Coinbase. This particular fund has to be spent in a certain way or it's invalid. But nowhere do we create money out of thin air. Yep, there we go. So, actually, I'll back up 1 second and just point out. So, again, that's a tax when you spend your coin. Tail emission would be a tax just kind of as a coin sits there. Do you agree that economically they're basically the same thing? Yes, there's subtle differences here, don't get me wrong, but they're basically the same thing. The value of your coin that you can get back diminishes over time, either because it's been inflated away or because you just got to pay a tax. Same thing. So, let's talk about the cost of security. Now, 50 years compared to a human lifetime is roughly the amount of time you could expect someone to be saving. I don't want to argue the exact number, but you know, you can agree with me. Like 50 years, say if you like start saying when you're 20 and you spend it when you're 70. I mean, this is kind of a rough number to, you know, wrap our heads around. Well, 1% compounded over 50 years is like 64%. But then again, you know, 0.1% compounded for 50 years is like 5%. I don't know about you, but you know, if I was spending like 5% of my life savings to go keep my life savings secure, this kind of seems acceptable. And again, this gets back to my point about if Bitcoin had tail emission to begin with, would we consider this acceptable? Well, we'd probably be all saying we're Austrian economists, and we'd make the analogy to gold. Economically, this is all fine. Yes, maybe 1%, you know, per year might be a bit excessive, but like there's some number where no one's really going to care. They're going to care for political reasons, but if Bitcoin had this from the beginning, no one would care. And the other way I'll go put this is, I mean, the Bitcoin price has gone up and down so much. Even like 64% really is irrelevant compared to price movements. I mean, even if Bitcoin was, roughly speaking, a world currency, like changes in the world economy would probably move its price more than so I should say its value, like say, you know, McDonald's burgers per Bitcoin more than 0.1% per year. I mean, this kind of stuff's a wash, really. Economically, it's just not that important. So, going back to tail emission for a second, I mean, should the Bitcoin supply be changed? Well, I like this Andrew Polster quote that I found quite a few years back, which is, and I'll repeat it on Twitter, the Bitcoin subsidy going down is a scary phase change. We have the system that seems to work, and we keep marching towards a type of system that we don't know works. We don't have examples of that type of system working. I mean, what altcoins out there even use proof of work for that matter? There are really not that many left. Now, that's not to say that proof of work is bad. It's just we don't have examples to go and learn from because Bitcoin's been so dominant in the type of coin that would use proof of work to begin with. And when you look at other examples, do they even have non-trivial transaction fees? Generally not. Occasionally they kind of do, but like it's notable just how broken transaction fee estimation is in nearly any other coin. Bitcoin's the only one that even has to think about this stuff. Yet, after all these years, and frankly in part because of things like Lightning and L2, L2s in general, we're pretty good at not paying transaction fees. It would be a lot more clear for Bitcoin's long-term status if we'd always had some kind of reason to create new blocks. And unfortunately, that's just not how Bitcoin's designed right now. Oh. Wait. There we go. All right. Anyway, in fairness to Andrew Polstra, he did follow up. I hate being on panels with podcasters. I'm worried they'll trick me into saying something stupid. Now, just to be nice to him, kittens aren't adorable. Like, you can quote me on that. I mean, look at that scary kitten. Very scary. Yeah, man. Yeah. All right. Well, anyway, so yeah. Thank you for that. And if we have time, I am happy to answer people's questions, including questions on something you'd rather have me given a talk on.
Thank you. So, any question?
You mentioned it could either be a question about this talk or something that I'd rather you have given a talk about.
Absolutely fine.
So I'm going to opt for the second one of the two. And I was wondering if you could talk a little bit about the scenario in the future that mempools are empty and miners would rather remine a block that has already been mined rather than continue forward.
In fairness, I think that's pretty similar to what I'm talking about here. So, you opted for version 1, but yeah, I mean, like, academics have studied this. And so first of all, I'm going to say it isn't necessarily fatal to Bitcoin, because one solution to that is you just change your practices to just wait for more confirmations. So from that point of view, maybe that's not a big deal. But the concern I have there is about decentralization. And that gets back to what kind of miner can intentionally try to reorganize blocks. Now, if I have 100% of hash power, obviously I can go do that. And at that point, it doesn't even really make sense for me because I'm going to get all the reward anyway. If I have 49% of hash power, there's a lot of circumstances where I can expect to get multiple blocks in a row. But the really important thing is if I have approximately 0% hash power, my chance of mining 2 blocks in a row is effectively 0. All right? Me finding a block with my miner sitting in my basement, heating my garage or whatever, for me, that's a windfall. And I'm not in a position to do clever things. But we want those miners. We want everyone to be mining in their home, ideally mining for themselves. The other thing is, let's ignore that for a second. Let's go look at where we kind of hope and think mining is going, which is things like P2 pool. Hopefully we're going to be able to reboot them and get miners back to cooperative yet still decentralized mining. Can P2 pool do reorgs? No. And there's just no plausible way where a thing like P2 pool could organize a reorg to then try to attack a bigger pool. And we might live in a world where hopefully P2 pool is like 30% hash power, yet because they can't do reorgs to go and get high fees, they're at a disadvantage. Now, it is true that sometimes there are very high fee events, and in theory this can already happen on Bitcoin. But at least it doesn't happen very often because subsidy is usually high enough that no one even tries. And one of the worries I have is this might be a matter of miners sort of organizing sufficiently to do interesting things. I mean, look at Mara as an example, which has Slipstream. That's an example of miners investing the effort to do something interesting to try to get a little more money. Now, Slipstream's not really a, I mean, all right, Luke's gonna argue differently, but I'd say Slipstream's not a significant threat to Bitcoin. But if that happens through reorgs that only large miners can do, this is a bigger and bigger problem. And we're much better in a world where this kind of situation doesn't happen.
Thank you.
Okay. Well, here, let me answer the first thing, which is, so demurrage as an economic concept, there's lots and lots of arguments in sort of the economic realm about what demurrage can do for currencies and so on and so forth. And I want to be very clear that I'm not making an argument based on economic arguments for demurrage. You know, there's many people who will say, like, you can boost spending if you're forced to spend money because it, you know, gradually goes away. And I mean, in the context of this talk, I'm going to say I don't care about that argument. It's just not relevant to what I'm saying. Maybe in the context of me getting a little drunk, I might go say this sounds kind of stupid. You know, I am, relatively speaking, an Austrian economist, but demurrage as a mechanism to go fund a particular thing that is a public good in the context of Bitcoin, that's what I'm talking about. And that's what I'm making an argument for. And if someone could hand wave an even better solution, great, I'd love to hear it. It's just I haven't heard that better solution. And believe me, I've tried. You know, I've come up with a bunch of kooky ideas to go pay miners too, but define realistic. So, I mean, just to make sure the audience heard, the question there is, you know, don't you think the most realistic solution to pay miners is high transaction fees? And my answer is, I mean, I was relatively for that in the past, but as time goes on, it just looks less and less true that high transaction fees will go do this. The other catch with this is transaction fees are inherently bursty. And the reason is, if I want to do a transaction soon, via mechanisms like RBF, or even just by observing what's in mempools, I can logically make the decision to pay higher and higher fees if the time between blocks happens to be long. And this is fundamentally a probabilistic thing. You know, there can be quite large periods between blocks because block finding is a Poisson process. It's just random. So there's certainly going to be situations where from one block to another, the next block pays much higher fees because there was just a longer gap. And that difference is very significant. I mean, you see this on mempool.space. If you just watch it and wait for a period where a block hasn't been found in a while, fees go up. Because people want to get in the next block and they got to outbid all other people who've created transactions in the meantime. It's a very natural thing. And I suspect that alone is enough to start triggering this problem.
Hey, thank you for your talk. I have two questions for you if you have time. First one, you made a claim earlier that whatever percentage you set for a tail emission, the rate of lost coins and the tail emission converge. Could you justify that claim?
I mean, this gets back to the math of that. I mean, you know, just to be clear, again, think of the leaky bucket. You have a certain amount of coins getting created, and the rate at which they get destroyed is proportional, and I should say the numerical value of the number of coins destroyed through loss is proportional to a rate. All right, so as one number gets bigger, the number of lost coins naturally gets bigger because your probability of losing a coin is not related to the number of coins you have. It's related, you know, it's a certain percentage of bad luck, basically. And that's why those two numbers will converge. And, you know, I'm not making the claim I know necessarily what those numbers are, but I can guarantee you they will eventually converge. I mean, it's kind of like, you know, if I go hold a golf ball and drop it, I may not necessarily know exactly when it's going to hit the ground if I didn't do a bunch of math and didn't observe much stuff, but I know it will, because that's just the nature of like gravity fields. You know, I don't need to know how high the ball is to know it's eventually going to go hit the ground. That's just what happens.
Thank you. Second question. You claimed later that the tax of a tail emission through inflation and the tax through demurrage, that they are equivalent. I think I'd like to clarify that there are some situations in which that's not true.
Yes, absolutely. So I want to be clear that when my use of the word equivalent there is, they're approximately the same. And a great example of this, I mean, let's just say hypothetically we set our demurrage tax rates like 50%. Clearly 50% is probably bigger than the rate at which people lose coins. I mean, just look around the room and like ask people how many boating accidents they've had. They haven't had that many. Well, all right, they have, to be clear, in case Revenue Canada is listening, but realistically they haven't. But if you pick a number that's probably close to what those rates are, the end result is probably going to be close to that. And you can certainly make an argument that maybe this makes the demurrage solution better and that you can kind of set a rates. But the way I would say that is I don't think the details of this matter that much. I think it's more important that there's some kind of thing that's better than this rate going to zero. And certainly, I think it's true that demurrage is something that actually can be implemented. Tail emission, hard forks are hard.
Thank you.
Ladies and gentlemen, Peter Todd.
Thank you.
Hi, I'm Leo. I regularly host the Vancouver BitDevs, and it was a great honor today to host Toronto BitDevs 001. We had a packed room, exciting conversations around economics and mining and Bitcoin, Lightning, ARC, all sorts of new topics. And there's a lot happening every month, so join a local BitDevs near you or start one yourself.
Thank you.
All right, you guys, welcome. My name is Isabel Foxen Duke. I am the host of the Bitcoin Rails podcast and the co-author of BIP 360. And really excited to moderate this panel about Bitcoin quantum resistance, the BIP Showdown, titled by Nifty. So why don't the three of you just introduce yourselves really quickly and just share a little bit about specifically what you're working on in the realm of Bitcoin quantum resistance.
Shall I go first? Hey, I'm Conduition. I'm working on a specification for the Shrink's hash-based signature scheme on commit, reveal, rescue protocols, and on isogeny-based post-quantum crypto.
Hi, I'm Nadav. I currently work at Chaincode, and I am working on isogeny-based signature stuff, and specifically I'm interested in kind of the functionality things like signature variants for having self-custody be possible and also having things like Lightning be possible and all that kind of stuff.
Hi, I'm Tadge. In quantum-y world, I'm working on recovery protocols. I gave the talk earlier today about lifeboat, life jacket, sort of how to get people who have not done anything onto a new system if we have to change how Bitcoin signatures work.
All right, so we're going to start with some low-hanging fruit, which is BIP 360, the first quantum-resistant proposal for Bitcoin. So right now, obviously BIP 360 introduces a new quantum-resistant output type, pay-to-Merkle root. There's been some debate on the mailing list about whether or not we should introduce a new post-quantum output type that's quantum-resistant, or if we should maintain Taproot as is and then simply disable the key path spend, when and if a quantum computer arises. This approach is otherwise known as pay to Taproot 2. I'm wondering if one of you wants to take a stab at kind of sharing each argument, right? Like just sort of like share with the group, like how you see this argument playing out on both sides. And then I'd love to hear from each of you kind of where you stand on that point.
I can have a stab at proposing both arguments and comparing them. So pay-to-Merkle root, or BIP360 as it's specified, has a pretty simple argument, and it is that if we get rid of the elliptic curve part of Taproot and just only use hash functions, and we just put all of our spending conditions into a Merkle tree, we get rid of the whole quantum vulnerable part of our cryptography, and the leaves of that Merkle tree, the spending conditions, can be either quantum vulnerable or not. It can be quantum secure. We could use some other signature scheme in that. And this enables us to spend Bitcoins without ever revealing a quantum vulnerable elliptic curve key. This is great because it allows us to just switch over to something post-quantum without any follow-up and without any secondary soft forks. However, there are still caveats. You cannot always be sure that your coins are quantum secure if you start sharing your elliptic curve keys or if you start reusing addresses where your elliptic curve keys are exposed. The other side of this argument is pay-to-Taproot v2, which proposes using essentially a clone of pay-to-Taproot where you still have an elliptic curve key posted on-chain and you can still spend with elliptic curve signatures. Now, this relies on a follow-up fork that would need to disable the key path spend in Taproot. And for this to work, you would need to do this before a quantum computer appears, ideally. But the trade-off is that the pay-to-Taproot v2 key spend is a lot more efficient than the pay-to-Merkle root elliptic curve signatures, because you don't need to include as much additional data as you do in pay-to-Merkle root. I think the exact numbers are 64 bytes for a signature with pay-to-Taproot v2, and under current knowledge, 96 bytes for a witness on pay-to-Merkle root with elliptic curves. Now, the pay-to-Taproot v2 argument is we want everyone to migrate to this as soon as possible, so we need to make the friction as low as possible to migrate, and then we can clean it up later with a follow-up soft fork. I've already given you the argument for pay-to-Merkle root. And my stance on this, my personal opinion, is that the pay-to-Taproot v2 option is admirable, but requires an assumption that we can accurately predict when quantum computers will appear in advance. If we can't, and if quantum computers appear suddenly, then our security is forfeit.
Out of curiosity, is there discussion about just having both of these things be true? Like just introduce P2MR and then also just disable Taproot keypath spends at some point?
There is. That's an option. It's a compromise that I think neither camp is really a big fan of because it reduces anonymity sets for more people because we have, 2 additional output types. And then you have the argument that the people on the P2MR outputs who are fully quantum safe would probably be concerned about a large chunk of the Bitcoin UTXO set sitting on quantum vulnerable outputs. Because if they get stolen in a quantum attack, that devalues the coins for people who did everything correctly. So really, ideally, we want everyone to be secure, whatever path we end up taking.
Fair point. Do Nadav or Tadge have any thoughts on BIP360 broadly or specifically the P2MR versus P2TR2 debate?
Yeah, I think one, it's on their own. You kind of have to have You kind of have to have the quantum resistant signature scheme also go with it. Like if it's just let's just activate pay-to-Merkle root and that's it. It's like no, you need to have shrinks or whatever in there. I am more sympathetic, I think, to the P2TRV2 because I guess my assumption is if you don't know ahead of time or very soon after it happens, everyone's kind of screwed anyway, and so. Because I don't see how everyone's going to move to these anyway. Maybe eventually, but I sort of think that like so many different things depend on being able to activate it in a reasonable amount of time that's not a huge worry for me. And the idea of like a P2TRV2 where it's just explicitly saying, hey, here's the explicit migration path. You have to use this inner key for like a hash-based spend, and then in the other case, you'd still need some kind of life jacket-like thing for all the pay to Taproot outputs. Taproot v1 outputs still there. So it's sort of like, yes, pay to Merkle root is cleaner, but like none of this is going to be clean. So that's sort of how I would look at it.
Nadav, any thoughts?
I don't feel like I have too many well-educated thoughts, but the first thing that comes to mind is that, like, it seems like there's at least some amount of tension between, like, do we optimize for a future where this happens in a very long time from now or doesn't happen, or do we optimize for a future where this might happen in like 5 years, or kind of there's a whole set of trade-offs that I'm sure vary what people would want to do based on how far away they think Q day is, if it's coming.
And it does seem like the split in opinions is sort of like roughly correlated with, you know, how far away people are concerned about getting this mitigation done. So I think that's a very good point. On the hash base, we'll get into signatures now. This is the meat of it. Signatures, we're going to spend quite a bit of time into the signatures portion of this panel. For PQ signatures, there seems to be some like loose, rough consensus forming, as far as I can tell, that people pretty much want a hash-based signature. Whether we, you know, add lattice-based or add isogeny, et cetera, at some point later on down the line is, you know, kind of more debatable, but there seems to be some rough consensus that a hash-based signature introduction would be a good idea. That said, hash-based signatures substantively reduce some of the amazing functionality that we get out of elliptic curve cryptography right now, and I'm wondering if each of you could kind of share a little bit about kind of what you're most concerned about on that front, and if you have any sort of ideas, or if you've heard of interesting ideas of like creative fixes or ways that we can address some of the loss of functionality that we may be dealing with once we introduce hash-based signatures.
Well, I can take a stab at this. So hash-based signatures don't really have much algebraic structure, and so you can't really do things like re-randomization or multi-signature very easily with them. There are some workarounds, like for example, you can use multi-party computation to kind of simulate a multi-signature protocol. It's a lot slower and it's a lot more involved and more complicated, but ultimately it is doable. It just takes a lot of work to get there. Another interesting workaround that has been being researched recently is signature aggregation using post-quantum snarks. Essentially, this would take a batch of hash-based signatures, which could be quite large, and a bunch of messages that those signatures sign, and a bunch of public keys, and just like CISA, merge them all together, except the mechanism for merging them isn't dependent on the elliptic curve discrete log problem. Instead, it just uses hash functions and either arithmetic or binary circuits to prove that a verifier checked all of those signatures. It's essentially a succinct argument compressing all of these signatures into one single object that is, I believe, logarithmic in the size of all of the other signatures.
We can just go down. Oh, Tadge, go ahead.
Oh, yeah, there's a bunch of things that you can't do, right, if this quantum computer or whatever elliptic curve break happens. And but on the other hand, like, we don't really do those things anyway. So it's like, oh, you won't get silent payments, right? Because you can't really do Diffie-Hellman. And it's like, well, silent payments is awesome, but I've never used a silent payments address. I don't, like, it's sort of this weird thing where we've had, and like, yeah, Frost is awesome. I don't think I've never used Frost actually with my own coins. And it's kind of this frustrating thing where we've been working on these kind of longer term, like, oh yeah, we want to have silent payments and Frost and multi-signatures and all these cool elliptic curve things. And we've been working on it for years. And then if it like turns out like, oh, well, as soon as we got it working, then we had to like stop using it. It's kind of frustrating for the people working on it. For the average user, they'll have no idea because they're like, well, I never saw that. So it sort of got cut off. The only thing I would worry is that there's a lot of people who, you know, reuse addresses and say, oh, I'm just going to use one address.
I just need to dig into this a little bit. Okay, so like I'm pretty concerned about lack of multi-sig personally. Like I would consider that something that's really important. Is your point of view then that something like MPC is like a reasonable enough fix?
Oh, no, I would say it's just the naive multi-sig where you just stick them together. So
like
I think
like op-check multi-sig.
Yeah, like, and that's, I mean, we don't know because people could be using Frost and Roast and you don't see it, right? have a feeling that 99% of the multisig happening in Bitcoin is just object multisig, which is like, ugly and it takes more space, but you can do that with all this hash-based signatures.
You can do this with hashed.
Yeah.
That's good to know.
Well, it's worth delineating between interactive and a non-interactive multi-signature protocol. Check multisig is a non-interactive protocol because all you need to do is sign the same message. Two different parties can do it independently. They don't need to talk to each other. The multi-party computation option requires a great deal of interactivity, just like musig 2, except a lot more rounds of communication.
Yeah, and also I think like BIP32 is something that a lot of people use as opposed to the other pieces of functionality.
Well, half of BIP32 works fine with hash-based signatures, half of it doesn't. Right? If your most significant bit is 1,
Which
yeah,
part
BIP32
doesn't
works
work?
People's, I mean, from the point of view where, like, for example, people share XPubs and stuff. People do those things if we're going off of what we do and what we don't do.
But the general, like, I want a deterministic wallet with a seed phrase and lots of addresses, you can do that fine, you just can't share XPubs. So, like, a lot of the uses that most people use, it's like, oh, it's fine, you'll never know. For the more advanced stuff, like if people are using multi-signatures like Frost and things like that, then yeah, that does get impacted.
Yeah, and I also think that it impacts, kind of like you said, what we're building towards. I mean, people are using Lightning today, and Lightning, unless you're running like release candidates or something, I don't know what the current stage is. I know it's been implemented on at least 2 of them, but have musig for the channels, but that's not something people will see because it's just Lightning to them. And similarly for adapter signatures. But with adapter signatures in particular, I think, for example, there's like an actual like privacy loss and some economically motivated, maybe like wormhole type attacks and things like this that could happen on Lightning. I mean, I agree they aren't happening, but that doesn't mean they won't, I guess. So.
It's more like cuts off things we want to do than the things we've already doing now. So it sort of, the future of Lightning is like, oh, well, we can't do these things we want to do, but we haven't really gotten there yet, and so that's sort of the frustrating part, where all these cool things we know are like a few years off of development wouldn't be able to happen. But you'd still have more or less today's functionality. So.
Could you just TLDR the impacts of hash-based signatures on Lightning specifically for the Lightning bulls? Like, could one of you just sort of explain how this is problematic potentially for Lightning?
In some ways, it's not that bad. Like, and I don't... There's like shrinks and shrimps and all these things. Lightning's actually in some ways a hard case because you're like, well, I want to use the same key and sign 1,000, 1,000,000 times, right?
Lightning wants to reuse addresses, basically.
Well, sort of, right? I'm not on chain, no, but between the two counterparties, yeah, I'm going to use this 1,000,000 times. And so that is not, that's a hard thing for hash-based signatures to do in one way. On the other hand, statefulness is okay because we're already stateful. Right? When you're signing in Lightning, you already know, oh, this is update number 23. This is update number 24. So like it's inherent in the process of Lightning. So the you don't need statelessness. So that sort of makes that, oh, I need to do 1,000,000 signatures, but hey, I know which number each one is when I do them. So this kind of works out great. So I'm not too worried. Like you do need to, it's very different from normal on-chain signatures and how you're dealing with it. But the downside and upside kind of cancel each other out. So it should be okay.
One thing worth pointing out is we've looked into how shrinks would affect Lightning and be usable on Lightning to a limited extent. But one thing that we realized is that no matter, with the way that shrinks works, no matter how large your tree gets, in a practical sense, you can't generate a tree large enough to be useful on Lightning unless Lightning has the ability to rotate keys when signing in a channel. So you could create a shrinks key with up to 1,000,000 stateful signatures or more, but every single signature you add to that, it costs in key generation performance. There's a way around this, though, with multi-tree XMSS. And this is a thing that we're hoping to look into more and assess how viable it would be for Lightning, because it's fully stateful, right. But like you said, Lightning doesn't care about that so much.
Yeah, minor note, but I assume it also does the thing it does for all Bitcoin transactions and makes commitment transactions bigger, which affects what kinds of payments might be viable over Lightning in terms of microtransactions and things like this. But
And then hopefully those never show up on chain, so the only final transaction is the cooperative close. So like when everything's working well, it really it's a ton of code to write. It's going to change, but for like the user experience, it's like probably they won't even notice if everything is coded well.
yeah, and then kind of one thing I mentioned earlier as well is that we will be locked into HTLC-based channels into the future, which has a few annoyances and maybe one problem.
PLTCs never, apparently, unfortunately.
Yeah, well, I mean,
well, we could still get it in 2 weeks.
Yeah,
maybe.
This is a bit of the shot in the dark, but I'm just wondering if any of you have done any research or are aware of any research into how this transition might affect non-Lightning layer 2s, BitVM, ARC, these types of protocols. Do you have any thoughts about that?
I'm too ignorant to make a statement on this subject
Say that again?
I'm too ignorant to make a statement on this subject, unfortunately.
Sure. Nadav, go for it.
Just off the top of my head, I mean, DLCs use adapter SIGs today. Even the pre-Taproot ones do.
There is a pre-paper DLC version that did not.
It's true, and not only
So,
that, but also
I
the
should publish that.
V-1 of DLCs. When the DLC spec was being written, we didn't have ECDSA adapter signatures until partway through. So we did do it in script. It's possible to do in script.
But that was still quantum vulnerable. I'm saying before I even wrote DLC, the paper, there was you basically make a giant table of hashes and pre-images, and the Oracle just releases one. It's really ugly, but you could do it. So
yeah, it makes things worse for, I assume, most off-chain protocols.
Yeah, that one is a significant on-chain. The impact is minimal, but the off-chain protocol does kind of blow up.
And the off-chain is already most of the constraint for, I think, practical DLC applications.
There are also some things that you can do with hash-based signatures that you cannot do with elliptic curves, though, and these may enable new schemes that we haven't thought of before. There is no such thing as a stateful elliptic curve key.
Yeah.
There are such things as a stateful hash-based signature key, and if constructed in the right way, it could be provable. So you could, for example, construct a specific key pair that it can only make one signature. That's never been done before on elliptic curves, as far as I know.
That's a Lamport sig, has that property.
Any
right?
one-time signature scheme.
Sure, yeah.
But it could be any arbitrary number. You could set it to 2 or 3, any number.
Yeah, I guess it's just funny in my head because when you're doing elliptic curve sigs, you're assuming hash functions are secure because you need hash functions in order to do elliptic curve sigs. And so any situation where we would want these kinds of functionality, we already imagine having them in EC land because why would we arbitrarily use EC for it if we already have it? Yeah, I don't know.
I have one final question for Tadge specifically on this topic because you mentioned earlier when we were chatting about kind of UX complexities around hash-based signatures. Do you want to dive? It's a little bit distinct from other functionality. What are your concerns around how these hash-based signatures will affect user experience?
Yeah, so similar to in Lightning, there have been people that have lost money where if you back up your Lightning channel and then use it and then restore and sort of forget that you used it or it used it automatically on some other computer, you can lose money that way. You could think of similar problems with stateful hash-based signature where you signed, you forgot you signed, it was in the mempool, but it never got confirmed, and now you're re-signing and potentially losing some security there. So there's potential problems. If it's so you need to be careful and clear with people that okay, use this in this way, use this software. Don't share keys among different pieces of software and things like that. Because there are, once you get stateful, people will find interesting ways that you didn't think of to oh, I didn't think you would do that. I never thought of that. Okay, you found a way to screw it up and lose money. Oops.
Okay, so that actually brings me to my next question, which is, I guess we can start with users. The question was originally designed thinking about wallet developers specifically, but we could expand upon that to all users, up until the end user. How are we going to ensure that people use this safely, right? We really are introducing a whole set of new risks that we just, assume we don't worry about today. What are best practices? What are things that we can do technically? What are things we can do on the education side, on the proposal side, to ensure that both developers are building wallets safely and users are using these wallets safely?
Don't reuse addresses. There are other things.
We're
of
really
course.
good at that, by the
you
way.
can actually,
we crush that.
There are sort of ways. So we say that a lot, right? And people still do. You can actually do a lot more, right? So you could make wallet software. You can't force people to use your software. Fine. So if someone wants to write software that just posts their private key in an op return, you can't stop them. So there's limits. But you could say, look, yeah, we have a stateful signature. And that's a problem because people don't keep track of state. But there is a blockchain. That's like a giant blob of state. And so you could do something that's very costly, and maybe there's better ways to do this. But like, hey, I'm going to scan the blockchain to see if I've signed before. And my wallet needs to be up to date and says like, okay, before I sign, let me see that I've never used this pub key before. And if I have, okay, I'm going to default to like the sort of longer path on shrinks.
You would also have to wait for the mempool to clear, maybe?
Or, yeah, give me access to the blockchain and mempool before I sign. And that's like a way I can, do it more securely. It's much slower, but if people are paranoid and they're like, look, I want to really make sure that I haven't done something weird and wrong. Okay, well, a lot of that data is available to you when you're signing.
What you really need in this context is an authenticated CRUD interface. Create, read, update, delete, right? But in this case, you don't really delete. You just kind of append because you want to keep track of this state counter. And if the state counter ever decrements, then you lose your coins. Now, there are a lot of different ways you could implement this, right? There's basically unlimited ways to store data in the world. A few that spring to mind would be, say, Nostr or the blockchain, like Tadge just suggested. There are also secure elements on almost every phone in this room which could do this. There's TPMs. You could call an authenticated cloud server. You could do a number of different things. And I think that the success of wallets in the post-quantum age, if shrinks is ever needed to be used, is going to be measured by the ingenuity by which people devise new ways to track state.
Hear, hear. Isogeny and lattices. Let's move on to non-hash-based signatures. Let's introduce some new cryptography, you guys. I'm going to just open this up to broad thoughts, like intro statements on isogeny and or lattice-based, one at a time. Let's hear it.
Lattice-based is fast but big and hard to maneuver into the schemes that we want to use. Isogenies are slow but very compact and risky. Hash-based signatures we've already talked about. There's multivariate schemes and code-based schemes as well, but let's leave those to the side.
Yeah, I mean, I think there are like different kinds of unknowns for the different schemes. Hash-based schemes don't really have unknowns, at least from the cryptography point of view, because it's an assumption we're already making, we're already comfortable with. If it's no good, we have bigger problems than signatures, even in Bitcoin. So I think, like, if you are using Bitcoin right now and you feel comfortable with the security, you should feel comfortable with the security of correctly using hash-based signatures. Now, with lattices and with isogenies, yeah, so I guess you covered some of it. One kind of unknown has to do with just like the assumption itself. Like, is the isogeny problem actually hard? Is the module learning with errors problem hard? What's the third one? Module shortest
vector problem?
Short vector problem, I guess, because it's an approximate one. Anyway, but yeah, and there's also like a bit of weirdness to kind of historically how much these problems have been studied versus how much time has been spent on like variants of these assumptions before we got to these ones. I think in lattices, a lot of people kind of talk about it as if it's very much older than isogenies, but like the current like more algebraic versions of the assumptions are, I think, less old than the original lattice assumptions, and they're required for getting like nice efficient things that we actually want. It's like even worse if you don't use these variants. But other types of unknowns include, for example, like isogenies are much more expensive. I don't think that they'll ever be faster or cheaper than the others in terms of computation time, but I think they will be much faster than they are today. Like hashes and lattices are both very optimized in modern hardware. Hashes are hashes, we already know about this, but lattice, like the actual operations on lattices is a bunch of linear algebra. Your GPUs do it really fast, your computers do it really fast. We've optimized like it very well. Whereas isogeny math is definitely not optimized in current software and current hardware. In theory, like it's very unoptimized. I think there are still orders of magnitude improvements to be had. Maybe not, but like very plausibly. But I still think like fundamentally it is still more computation than the others. It's just a question of like how much more was another thought.
I mean, I'm not an expert on both of these, but it does sort of seem like get some shrinks kind of thing in soon, and then, yeah, maybe if we need it, like, it sort of feels like if the whole thing is like we're worried we'll need something. Okay, well, shrinks is something, and it's pretty good, and we can have it. And then if we never actually need it, then we probably are not going to fork in isogeny or lattice thing. But after we have started saying, okay, now we do need shrinks and people are using it, then seems like a good time for like, okay, well, elliptic curves are gone. Now we just have hash-based. Hey, we liked all the cool things we could do with elliptic curves. Now maybe we can reintroduce, you know, a lattice or isogeny-based scheme for the people who want to do fun stuff.
Yeah, I mean, I will say on a super long term, like once, you know, I mean, like in 100 years, the amount of confidence built in these new assumptions is going to be very similar, assuming that they hold up to what we have in EC, even if there's no quantum computer, or yeah, I guess especially if there's no quantum computer. And I mean, I remember hearing conversations and participating in them occasionally before post-quantum was really a thing people were thinking about, and it was not a thing I was thinking about how it might be nice to have lattices for certain kinds of functionalities that we don't have with elliptic curves, and maybe like we can get better ZKP type stuff or other things that we might want. So I think there's still like, it's interesting to research isogenies and lattices whether or not quantum computers come around. I think in terms of long-term kind of what we would want. But I agree that like in the short term, I probably wouldn't feel comfortable with anything but a hash-based scheme. And in the long term, we might want these things anyway, so we should look into it.
Oh, go ahead.
No, I was just going to agree with Nadav that that's exactly the greatest motivation for hash-based signatures, is that they give us this cushion of time in which we can spend more time researching the other more advanced schemes and improving the state of the art. Anyway, that's all.
I'm curious, Nadav, if you wouldn't mind kind of going into a little bit more detail about the isogeny break that happened in the semi-recent past, because this is regularly cited as the reason why isogeny is like an absolute no-go, maybe for the rest of time. Other people say, you know, oh, this break had like these things that actually make it not that big of a deal. What's the deal with the isogeny break?
Yeah, so it was a protocol called Psych, which was basically Diffie-Hellman for isogenies. What's the S?
Supersingular.
Supersingular isogeny key exchange, Psych. And it was very broken, but it sat around for like 10 years, just as like here is the fastest, best key exchange that we have based on isogenies, before someone was like, whoa, I can break that on my laptop. And I think it does demonstrate something that's kind of a risk about isogenies. But an important thing to note before I talk about that is that it is not based on the isogeny problem. It is based on a weaker variant of the isogeny problem. And it just so happened that it was like the isogeny problem, but where you have this extra information. And what ended up happening is it turns out that little bit of extra information is enough to recompute the private key. So that is what broke. And funny enough, it also kind of introduced cryptographers to the idea that like you only needed this little bit of information in order to represent private keys. So it led to a bunch of efficiency gains in other isogeny-based schemes because now we have all these other mathematical tools that are kind of like more compact and have various other kind of properties to them. So this attack really kind of benefited like the signature schemes because it gave us some algorithms that helped us in the context where we're not sharing this information just locally, representing things. But yeah, so first of all, it's not actually based on the same assumption. It's like a strictly weaker, actually completely broken version of the assumption. So it broke, but there's no reason to think that it breaking should mean other stuff is broken. But it does kind of demonstrate how, like, as a not well enough studied kind of set of algorithms and set of objects, and also they're just kind of like much more complicated and less accessible, I would say, than lattices and especially than hashes to people with, I guess, more cryptographic backgrounds and applied backgrounds. It's like very plausible that things could change in a similar way where someone who, knows a bit more of the math or, uses AI or just does literature review themselves and finds another result from the 1970s that just trivially breaks something that we're doing. But I do think that I'm much more confident in, okay, I came into the field after the psych break, so maybe I'm like a little bit biased. But when I look at the assumption that psych was based on, I definitely would imagine I have much less confidence in that than I do in the actual isogeny problem.
Well, even before psych was broken, people thought that it was those torsion points. Those are the extra additional data that you were referring to. Even before psych was broken, people expected, if that's how psych breaks, that's how it will break. And it turned out that they were right.
Yeah.
I think you are kind of bringing up sort of like a broader, interesting point here, which is that, okay, even if the isogeny problem is sufficiently hard, right? Like there's so many weird edge cases of like, well, what if in this situation or in that situation we get this extra info or, whatever. Just weird parameter question marks that we don't understand yet just because these things are so new, potentially, that makes them fundamentally more vulnerable, even if the underlying fundamental math is hard, right? I mean, that's sort of what I'm hearing.
Yeah, and especially as a mathematician might correct new to us as cryptographers, not necessarily new math, but we don't necessarily know everything that's happened in the last 100 years of algebraic geometry.
Do you see similar challenges with lattices? I mean, is that sort of how you view the fundamental security vulnerabilities of lattices, or do you think that, lattices are just not problematic at all? Are there security vulnerabilities? Where is the security-specific research question around lattices?
I don't really know about lattices, but what I can say is that, well, the rest of the world is already using them, and it'll just be every phone, every web browser, every server in the world in the next few years will just be using lattices everywhere. And so
with hybrid cryptography.
What's that?
With hybrid cryptography.
Sure, with hybrid. Well, some.
Key point, fair point.
Some will, but so to some extent, shrinks is a Bitcoin thing. It could have been written by other people, hasn't been, but Bitcoin is a sort of weird use case where it's like, no, we really want small signatures and short, and we want this. But I think what will be nice is we probably don't have to work that much on lattices because everyone else will, and we can take what they do. So I think if there are a lot of cool new things that come out of lattices, I would expect it to not be on this stage, but maybe a much larger, fancier stage at some conference with thousands of people, because I feel like the giant tech industry is going to be working on that, and so that's good. Hey, we can use whatever they come up with.
I'd like to just comment on the state of the art of lattice-based multi-sig schemes and re-randomization schemes and threshold schemes. These are all advancing rapidly, and this is part of why having that time cushion is great, because maybe someday someone will have an efficient, compact, lattice-based signature scheme that gives us all the features we want. And that would really be the ideal case, because then we could benefit from all of the work done in the greater cryptography community and still have all the features that we need for Bitcoin.
Other than maybe size. I guess how I think about lattices, I think the actual like underlying math is more accessible today. I'm not sure that I would claim that it's like fundamentally easier, but it's at least very obviously closer to math that more aligns with like standard background, like, you know, linear algebra stuff and things like that. Maybe a little bit of calculus-y stuff as opposed to like scheme theory or something.
Compared to hashes, specifically.
Oh, no, compared to isogenies, sorry. Yeah, hashes are just pure CS, no math required, which is a benefit and part of the reason why it's hard to do things with them. But yeah, so in terms of lattices, I think like the type of break that happened for something like Psych is much less likely to happen, where someone's like, oh, there's this ladder's result that like nobody understood, just like applies here and does things. I mean, it's possible, but I feel like it's much less likely. I will say though that the current lattice assumptions are like variants of the original one that are weakenings. And so I still sometimes worry, and I have an outdated view of the current state of cryptanalysis on the difference between these weakened assumptions and the original ones. But like the original ones are things that sound very plausible. Like it's hard to find short vectors in a really high dimensional lattice that you don't have a good basis for. Is like, once you think about it for a bit, you're like, yeah, that seems really hard. And then it's like, but what if there was like some extra algebraic structure to the lattices? Is it still hard? And then these are the kinds of assumptions that we are actually using. So there could be something plausibly where like the assumption breaks because of the way we've weakened it a bit, like happened with Psych. But yeah, I don't know.
I also want to mention that there's a very great gap between the implementation complexity of these different signature families. At the very easy end, you have hash-based signatures where, you know, any amateur can implement them in a weekend without much experience and just by reading a spec. Then you have lattice-based signatures. They're a little harder and they require a little more math background, but ultimately, you know, stuff about linear algebra is available online. It's not that hard to understand, especially with like in the age of YouTube, we can very easily look at visualizations and, you know, form an intuition for how these problems work and how the signature schemes work. And then at the end, you have isogenies, where you kind of need a doctorate to be able to make good arguments about security.
Yeah, I will say that I think I agree with the characterization, but I also hope and actively work to change that picture of how things are. I can imagine in 15 years, it's not that much harder to learn what you need to know in order to do Bitcoin stuff about isogenies than it is today to learn about elliptic curve stuff.
Really quickly, I'm wondering, Tadge, if you could just sort of address the role of recovery protocols in this whole quantum mitigation situation. Like, what do you see as the role of recovery protocols and why?
I think recovery is very important because people I think it would be a mistake to think, oh, well, we've got this new hash-based signature or whatever, I can move all my coins to it, I'm safe. Like, that's not really how Bitcoin works, because if you're safe but no one else is safe, well, your Bitcoin aren't safe, right? It's maybe on a technical level it is. Like, I've got the last unspent Bitcoin output and all the rest have been compromised. It's like not a useful system at that point. So that's sort of the hard part with a lot of this, is it's not just enough to protect yourself. You kind of have to protect everyone, or as close to everyone as you can get. And given the success we've had with like getting people to use new addresses every time and getting people to, you know, migrate to SegWit and Taproot, yeah, people do whatever they want. They're not going to listen to you. We can tell them, you will lose all your money and you need to not reuse addresses and you need to upgrade to this new pay to Taproot v2 or something. And like, some people will, but a huge amount of coins will not.
And so I feel like this is why you need some kind of recovery thing that, like, there will be millions and millions of Bitcoins that just don't care, don't listen to anything you're saying, and just keep doing what they're doing and have been for a decade. And so it's some kind of plan for those.
And not just will not, but also sometimes cannot.
Who knows what they're doing? Yeah.
The nice thing is that thanks to the work of people who built the schemes that our wallets rely on today, we do actually have some of these baked-in knowledge asymmetries where we have secrets that the CRQC, the quantum computer, can never know as long as we haven't exposed them publicly, on Twitter or something.
Or on the blockchain.
Yeah, or on the blockchain, like in the case of public keys. But this is really kind of a saving grace. Like, not every blockchain will have this.
I mean, some are in fact, some yes, and some are the opposite, in that generally with, 25519, part of the standard, it's not detectable, you can't enforce this, but the standard is you take your private key, you SHA-256 it, and then you start doing multiplying by G, you do your multiplication. So in the actual code is like a SHA-256 step right before, and so it's like, ooh, that's nice. Essentially every scalar is a hash. You can always go back. So there's some schemes like that where it's like, oh nice, if you're using 25519, you kind of get this always.
Why is that helpful if they can just use the hash?
The idea would be your private key, whatever private key you give to the sign function immediately gets hashed. And so the quantum computer would not be able to reverse that SHA-256 step. And so you could prove it. You could say, the quantum computer gets to the scalar, but that scalar wasn't actually what I threw into this function. I threw into something else. And so I have a pre-image of that scalar.
Got you. So the idea is maybe you can prove over SHA or something.
You prove, I know the pre-image of this.
It would suck to have to do that on chain, but I guess it's better than nothing.
Oh, it's 32 bytes. It's no big deal. Yeah.
For SHA proofs?
It's just your private key is 32 bytes. You throw it in the function, it immediately gets hashed, and that's used as the scalar. And so it's like, oh, I just give the 32 bytes.
Yeah. I meant for the recovery, when you have to prove it without doing things, it would be a ZKP that the hash
so
tree.
you would do it sort of like the lifeboat thing I said, where you just you say, look, all these private keys are useless now anyway. I'm just going to show I know a pre-image of it, and I can commit and reveal it that way.
Got it. Okay.
Last question for Tadge, and then if there are any audience questions, I'd be very interested in hearing them. I'm curious earlier we had also mentioned, you had talked about that there may be a role for recovery protocols in potentially preventing the outcome of lots of forks, right? And just consensus breakdown in some of this. Could you kind of explain why that might be the case, or what the role of recovery protocols might be there?
Yeah, so if you get a lot of people to sort of agree, this is a nice compromise, then maybe you don't have as large of a incentive to fork off. If the choices are, let's let all these coins be stolen, or let's let all these coins, let's destroy all these coins, that's a very philosophical, I don't think arguments aren't really going to work, right? You have your idea. Whereas it's hey, here's a third way where most of the time, people can recover them. And yeah, a few % will be destroyed, unfortunately, but for most of the cases, people get to keep their coins. I could see how some from both sides are oh, well, okay, that's a good compromise in the middle. So maybe people don't get as much momentum to try to split into two groups. Who knows?
I like it. I'm very pro recovery protocols right now. Questions from the audience? Anyone have questions about PQ cryptography or anything related to the post-quantum transition?
Do you guys think there's ever going to be a reason to activate an isogenes-based signature in the absence of a quantum computer actually existing?
That's a good question.
I think I would file that under, I don't think we know what we can do with isogenes yet. Because isogeny signature, the first signature scheme based on isogenes is from 2020. The assumption's older, but the first time we did a nice signature with it was 2020, and 2024 I think is the current state of the art. So and that's just for signing, with no extra funny business. So I think we won't know for a bit what cool things isogenes might have in store. Hopefully we find out And then depending on whether we can do cool things with them, I guess that's a discussion. It's probably still a harder sell than lattices, but maybe in 10 years it won't be. I don't know.
Yeah, there would need to be some feature that would be exclusive to isogenies that elliptic curves could not do in the non-quantum future.
Yeah, although, you know, if it's uncertain either way, but we don't think we have them right now, maybe it's still a benefit.
In the back. Russell?
This question might show my bias here, right? So there's been talk about maybe we'll fork in isogenies, maybe we'll fork in lattices. Just interested in the panel's opinion on, like, what if we had programmable money that allowed people just to select their own method of securing their coins?
I guess my first thought would be kind of similar to something Tadge just said, which is, like, if you think isogenies are secure and you don't think, like, you think lattices are probably insecure, it doesn't, like, you don't want to be sharing a chain with a bunch of people who are using lattices, because if you think that all of their coins are vulnerable, then yeah, it's kind of, yeah, I don't know.
It comes down to what is prescribed for the average common user. And if we prescribe the average common user to roll their own crypto in a homebrewed script, it's not going to be surprising if most of the UTXO set ends up stolen and in the hands of people who know how to better manage their cryptography. And if we prescribe a well-certified and verified signature scheme constructed out of the most reasonable and consensus-agreed set of assumptions, then I think there's a very survivable future for Bitcoin in any context, quantum or non-quantum.
It's a hard one because on the one hand you want to give people freedom and give wallet developers freedom. At the same time, it's sort of, I guess a good example is OpenSSL, where they're like, hey, which cipher mode do you want? Do you want ECB or do you want CTR? ECB, oh, you just lost everything. ECB was the wrong choice. Like, why did you give people the choice of ECB, right? And so it's kind of like if you ask people in their wallet, like, well, which want isogenies or lattices? Like, who can answer that? Like, maybe a couple of people in this room can answer it, but almost no one using Bitcoin could meaningfully answer that question. So it's a hard one where you want to give people freedom, like agility, like that's cool, but at the same time, you definitely can't show users this kind of thing. So.
If we wanted to, say, prescribe a certain signature algorithm that uses programmable features in order to implement it, I'd say that's probably fine. I mean, you're probably going to end up with witnesses that are way larger and slower to create. It's going to be more complicated, clunkier. But still, that flexibility might be a valid argument, because then you could transition to a different scheme later more easily. There's pros and cons to both, basically.
Yeah. I'm still not sure I would want to share a chain with a majority of people using some version of script to roll your crypto. That would be very scary to me.
What if we all publish our private keys on chain just to spite you?
Then I guess I have to go sell my Bitcoin.
I think this is an important point that you brought up, though, that I've heard others make, which is essentially like this idea that, like, if we can all just choose the signature that we're each individually comfortable with, like, let's just let people choose, is sort of like based on this false premise that, like, if my coins are secure, then my money is fine. But the truth is like, if everyone's coins aren't secure, then my money's gonna be worthless. So, it's kind of like a moot point, doesn't really matter. Like,
I mean, the reality is that we're going to have that choice either way, whatever Bitcoin adopts. You can always sell your Bitcoin for something else that uses a different assumption. You could sell your Bitcoin for, I don't know, dirty fiat that uses lattices to secure all the bank networks, right? Or for whatever Ethereum's going to end up using. There's a whole wild world out there. And Bitcoin is generally quite conservative, so I expect that we're going to go with the most conservative option because that's the one that most of us can all agree on in a very rough consensus environment.
Yeah, I will say, like, there is still the potential to do hybrid things where, so long as they're not both broken, then things can be fine, but there are costs to doing so. So that can make it
Like
harder.
financial costs? Is that the main?
No, like space and time costs. Like it's less efficient to basically sign in a bunch of different ways at the same time and then have to embed all of that data. I mean, I'm simplifying things a bit, but yeah, I mean, basically, there are hybrid signature schemes where like, so we take multiple signature schemes, mash them together, so long as one of them isn't broken, you're good to go, but then like the more you throw into the pot, the worse the actual signature is. Yeah.
A very, very last question here.
Hello, yeah, thanks for the talk so far. And my question is, with there being some signature methods that are insecure and how to decide between a newer method being adopted, if something is insecure and people are actually able to steal those coins, well, they're going to steal them and transfer them to the secure method is like what they would probably do. And so would that just be the indication of, okay, whoever is stealing the coins and transferring it to a different address, that's the one we should probably switch to? Would that be our answer there?
I don't think that expertise in building a quantum computer will have much correlation with expertise in which new assumption is less likely to be broken by a quantum computer, because they're kind of very different fields, so to speak. So I don't think we should think that they have privileged information like that. I also would just note that like they could also maybe more easily steal your coins by sending them directly to Coinbase, so it's not their liability anymore, and then just claiming fiat or something. So there's no guarantee that they would be moving onto post-quantum and keeping it inside of Bitcoin, for example.
Awesome. Thank you guys so much. This was really fun. And yeah, I think that's it for the day. Were we done, Nifty? Is this the last one? One last thing. Okay.
Yeah.
Here we go.
Okay, Chris. So there's a lot of people in the BIP 110 community who say that Bitcoin covenants do not make it better money and it's used for non-monetary use cases and spam. Could you address this?
The regular Yeah, I mean, I think with any new feature that we add to Bitcoin, there can be unintended consequences. So we saw this with Taproot, obviously, and SegWit. So if we turn on covenants, there could be unintended consequences. However, if we activate BIP 110, that will show that we can fix unintended consequences when they happen. So, I don't think we should be scared of covenants. I don't think we should be scared of covenants.
Do you think that the non-monetary use cases of covenants would be overwritten and prevented if BIP 110 was activated first? Is that like a prerequisite?
Well, yeah. So I think that what BIP 110 achieves in part is a sort of a cultural shift of being friendly to spam towards being hostile to spam. And so by spam I mean non-monetary use. And so in my opinion, yes. If we start activating, if we just keep activating stuff and we never deal with the unintended consequences from the stuff that we activate, we're just going to build up a bunch of cruft and entropy in the system, and it's just going to decay.
Yes.
Right? So BIP 110 is a cleanup. It's like, all right, we have these issues that were unintended. Nobody foresaw these, so we're going to clean them up. And that's going to I think that's going to restore confidence in the devs, It's going to be like, okay, the devs had a, mea culpa, they messed up. We fixed the problems. Now let's activate something new. I feel like BIP 110 is sort of like the path towards that, There's people in the NOTS camp or BIP 110 camp that are against covenants, but I think they just have a sort of spidey sense about covenants because of how anti-filter the pro-covenants people were when they came in, when they showed up after CTV failed the first time. So why did you ask me those questions?
Because I made a talk
in Vienna.
Now
And I
I
said,
can
do
see
covenants make Bitcoin better money? And I think the answer is yes. Covenants do make Bitcoin better money.
Absolutely. Covenants make Bitcoin better money. I completely agree with this statement.
And can you tell me what are the monetary use cases of covenants?
I mean, so the thing that I'm excited about with covenants is that you can do CTV and CSFS, which enables LN symmetry. LN symmetry is awesome. It lets you not have to there's no penalty. Like you can just put your money in a channel, and if an old state is published, you just publish the newer state. and then it closes. Like there's no penalty. There's no getting accidentally justice. There's no like, oh no, I lost my backup. You just need the most recent state. That's all you need. So you don't have this giant database that gets all filled up with old states. And the really important thing about LN symmetry is that watchtowers actually finally work. Right now, a lot of people don't use watchtowers because they kind of don't scale. Yeah. Covenants, I fix all of that. And also covenants help with ARC. I don't fully understand how they do that. You super explained it to me at one point, and I don't understand it. I did understand it, but I don't remember it.
Lightning alone.
Just lightning. Yeah, lightning is. People are always like, "Oh, lightning is so disappointing." It's like, yeah, but if we just had covenants, it would be way less disappointing. It would be awesome. I would never out of nowhere. Yeah, LN symmetry is epic. And covenants are epic, and the stuff that we could do with them is magical. And we should definitely, yes, we should be worried that there might be unintended consequences, and we should be careful when we design these features so they don't cause unintended consequences. But if we're willing to acknowledge that there were unintended consequences and fix them, which BIP 110 sort of sets a precedent of that, then I think we're going to be totally fine.
Perfect.